Yes.
Okay, so good morning, my friends. I'm Subramanya, one of the organizers of this edition of ST4 2020. So, on behalf of all the organizers, let me welcome you to ST4 2020. And as you know, we had finalized IIT Kanpur as the venue this year. Every thing was taken care of, every details was taken care of. But like the rest of the world, we too needed to adapt in the face of a global pandemic. And it would have been too easy to cancel or drastically postpone this year's ST4. But all of us were of firm conviction that even an online version of ST4 will continue its success story. And we asked for your support a few months back. And it's a testament to the spirit of our community, of our passion for learning, and of our bonding that we are here today. And in fact, in Slack, we are 100 members strong. There are already more than 50 participants on the Zoom. And we are joining here today from literally all over the country. People are stuck in media predicaments. Some of us are in our homes, some are in our relatives' home, some are perhaps at their friends' home, some are still at hostels in their institutes. And wherever you are, I hope you are well and you continue to stay in good health. And on behalf of all the organizers, let me welcome you once again to ST4 2020. So let me remind you once again about some protocols that we should follow during the Zoom lecture sessions. So first and foremost, please keep your video off at all times. Sometimes depending on your settings, you might have your video on by default when you join. Please be mindful of that and please turn off your video and keep it off at all times unless specifically asked by one of the organizers or one of the moderators to turn it on for some reason. So while the lecture is going and if you want to ask a question, please unmute yourself. Please say that you have a question and wait for the speaker to acknowledge that interruption. Otherwise you will be speaking over the speakers and everything will be sort of gibberish. So once the speaker acknowledges your interruption and gives you the green light, go ahead and ask your question. And the questions need not be short or precise, anything. Ask anything, ask in details, ask about anything you like. And if you're not satisfied with the first answer, you can keep on asking it again. And if while a question answer session is already going on, if you have a follow-up question or a new question, please don't unmute yourself and interrupt the conversation. Just use the raise hand feature on Zoom. If you don't know how to do that, on your Zoom window, there is a tab called participants. If you click on that, a small window opens. And on that window, there is an option called raise hand. If you do that, all the hosts and the co-hosts will be able to see that you have raised your hand. And in a proper time, we will call on you. Then you can unmute yourself and go ahead and ask the question. If you have any technical question, like you're facing some internet problems, connectivity problems, please ask them in chat. Don't unmute yourself and ask it in over voice. So you can also, if you will note that all the co-hosts include a speaker and the team of moderators. And at any time you are asking questions, most of the moderators also can write on Subbu's iPad screen. So if you need to ask for their help, you can definitely call on a moderator, or you can just simply say that any of the moderators, can you please help? And so that's it. So if there are any pressing question at this point, you can ask in chat. Otherwise, we are almost due time to start our lectures. So without any further ado, let us start with the lecture series of this year's ST4. Our first speaker is Subramanya Hegde. He's a postdoc at HRI Allahabad, and he will be teaching us supergravity. So Subbu, over to you.
Yeah, hi. So let me turn on my video. Okay, so can you see me now?
Yeah.
Okay, yeah. So firstly, I have a few things to say, which is non-academic. So firstly, thanks to the organizers for organizing this online edition, because I'm sure it took a lot of effort. And as a previous organizer, I know that these things are hard to coordinate. And many of them may not even be in favorable conditions. So thanks to the organizers. And secondly, something that is related to us being a community meeting at a conference. So of course, many of us are, exercising our privileges by being a part of a conference and so on. But I hope this does not serve as a factor which will further stress out people, thinking they have to work the hardest during the pandemic and so on. But instead, I hope this event will act as a support system where people, if they're frustrated, they can talk to each other, just like a conference where they can meet each other and share each other's frustrations and excitements and so on. So I hope on Slack, people also say hi to each other informally over private messages and so on. So with that, so let me start my lectures. So these lectures are on supergravity. And first I'll say a few things to motivate these lectures, and then we will go on with the basics. So supergravity is a theory of gravity with supersymmetry, and we will learn what is supersymmetry later. And it is interesting because it is the low energy limit of superstring theory or M theory. And computation of black hole entropy, the microscopic black hole entropy from string theory, and then comparison with supergravity results is a major consistency check of string theory, because the leading area law of the black hole entropy should be true in any black hole for string theory. And this is a very powerful consistency check, and it is one of the triumphs of string theory to have shown this. And there are also lessons that higher derivative corrections to black hole entropy, what they can teach us. And also recently in ADS-CFT correspondence for corrections to the leading order result from the 1/n expansion of black hole thermodynamics, there have been relations, there have been efforts to compute it from higher derivative terms in supergravity. So all these things will come up later some of these things will come up later in the lectures. But the central slogan of these lectures is that if somebody, I'm sure that all the participants of this conference know how to construct a general coordinate invariant Lagrangian. For example, to show that Einstein-Hilbert action is diffeomorphism invariant, I'm sure everyone is able to do. And of course, there might be many people in the audience who, if given a bosonic sector of supergravity, they can see the bosonic action and study the solutions just like one studies for general relativity, barring a few extra techniques that come up. But if you look close enough, and if you ask how are these theories constructed, and fundamentally what are these theories, then at the classical level, what is true is that, at the classical level, what is true is that physical supergravity theories are constructed as broken conformal supergravity theories. Okay. So this is the slogan of these lectures. We will first construct conformal supergravity theories, and then we will do some gauge fixing, which will break some of the conformal symmetries, and then we will obtain Poincare supergravity theories. Okay. So this is the slogan of these lectures. Okay. But of course, to understand this, we need to know, we need to study many of the basics, right? So namely, we should know a bit about spinors, and we should understand supersymmetry, its representations, and we will need to understand how to look at gravity as a gauge theory classically. So we will go on with these basics. So our approach will be humble in the sense that we will set all our basics right. And I am sure, the calculations are horrendous, but I think everyone in this audience, once they know these basics, they can go home and compute conformal supergravity invariants. Okay, so so these are the plan of my. Yeah.
So one of the audience is requesting that if you can hide your drawing tool so that the screen is a bit filled up. So the way to do that is that if you touch that pencil icon on your right top of the screen, it will just hide the panel, and you can keep on writing with the current tools. And if whenever you want it again, you just once again tap the pencil.
Okay, done.
Thanks.
Okay, yeah, sure. Okay, are there any more questions? Okay, so let me continue. So the plan of my lectures were already posted on the Slack. So, but to summarize it briefly, so we will first study spinors, and then we will study supersymmetry, and then we will study supersymmetry representations, then superconformal algebra, and then without supersymmetry, we will see how conformal gravity theory can be constructed as a gauge theory, and how it can be gauge fixed to obtain Poincare gravity theories. And then we will go on to see some details of n is equal to 2 conformal supergravity and how it can be gauge fixed to obtain Poincare supergravity theories. And in the end, we will hopefully look at some new constructions of higher derivative invariants and some basics of supergravity solutions. So this is the plan of the lectures. So let us start with Clifford algebra. In 4 dimensions. Okay. So our goal in this lecture is to understand Majorana spinors in 4 dimensions. And I'm sure much of this lecture, many people are familiar with, but feel free to stop me at any point. Okay, one more disclaimer I would like to add is that in these lectures, we won't discuss the quantum feature of supergravity theories or supersymmetric gauge theories and so on. So the subject of supersymmetry is very vast, and our aim will be to understand classical supergravity constructions. But please feel free to ask me anything, and if I don't know, someone else can answer. Okay, so let me then begin. So we will use the metric convention minus, plus, plus, and throughout these lectures, we will work in 4 dimensions. Okay, and so as all of us know, Clifford algebra is defined using gamma matrices. By this relation. Why are we interested in this relation? Then of course, we know from Peskin that suppose there are matrices, 4 matrices that satisfy this relation, then that implies that there exists a sigma mu nu, which is 1 over 4 gamma mu gamma nu, which satisfies the Lorentz algebra. Okay. And of course, we know from our quantum field theory course that in quantum field theory, single particle states are irreducible representations of the Poincare algebra. So it is interesting to study representations of the Lorentz algebra and what are the fields that we can write using representations of the Lorentz algebra. Okay. So that is why Clifford algebra is interesting. Now, of course, if you look at this relation, then given a gamma mu, which satisfies this relation, then we can define a gamma prime mu, which differs from this by a similarity transformation. Okay, because if this satisfies the Clifford algebra, this will also satisfy the Clifford algebra. Okay, which is easy to see. Now, in these lectures, we will restrict ourselves to what are called as Hermitian representation. Okay, and they have the relation gamma mu dagger is equal to gamma 0, gamma mu, gamma 0. Okay, if you use the first anti-commutation and this together, then you will see that gamma 0 is anti-Hermitian and gamma I for the space indices, they are Hermitian. Okay, so for simplicity's sake, we will restrict ourselves to Hermitian representations. And in this case, instead of S gamma S inverse, we will have S gamma mu S dagger. Okay, so we will have a unitary basis change. Now, of course, this basis change is between equivalent representations. So it can be shown, but we will not show in these lectures, that given any dimension, then and at least in 4 dimensions, there is only one irreducible representation of the Clifford algebra. But of course, once you have an irreducible representation, you can construct equivalent representations. And that is done using this transformation. Okay. Are there any questions? Okay, let me continue.
Hi, Subbu, I have a question.
Yeah.
So at any point, are we going to need explicit representations of these gamma matrices, or is it going to be largely implicit, like any choice will work?
Okay, so we will take a mixed approach in these lectures, in the sense that many of the ideas I will introduce using an explicit representation, but the language in which it is written is so that it can be made representation independent. It's purely for the sake of time.
Okay, thanks.
Okay, so let me continue. So now, with these gamma matrices, one thing we will notice is that, So firstly, let us study a particular representation, which is called as the product representation. Okay. As I said earlier, to save time and not to drown ourselves in Clifford algebra and general dimensions, I will introduce everything using a specific representation. But of course, the way it is used is so that it can be generalized to any representations, and we will discuss it whenever relevant. Okay? So consider this representation, which I am sure many of us are capable of constructing. All of us are capable of constructing because we know Pauli matrices. Okay. So this clearly is a representation of the Clifford algebra. Basically, we are just using the fact that all these Pauli matrices, they anti-commute. Okay, sigma I are Pauli matrices. And this I is there, imaginary I, so to ensure the space-time signature when you take the Clifford algebra. So this is one representation of the Clifford algebra. And this is also a Hermitian representation because all the Pauli matrices are Hermitian. Okay. So this can be checked. And yeah. So now what we have done is we have defined these matrices, which are gamma mu, but then they don't really close under multiplication, okay, which you can see with this specific representation also. You can construct various matrices. For example, if you multiply gamma 2 with gamma 1, you will get sigma something proportional to sigma 1, tensor product sigma 1, which is not a member of this set, right? So these matrices are not closed under multiplication, and therefore we will define what is called as a complete Clifford algebra. So the complete Clifford algebra contains identity, because identity is on the right hand side of the Clifford algebra, gamma mu, which we already have, and then gamma mu1, mu2, which I'll soon define, and so on, and gamma mu1 to mu4. Okay. So basically this dot 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 is gamma mu1, mu2, mu3. Okay. So what are these matrices? So these matrices are antisymmetric combinations of gamma matrices. Okay. So the reason being, suppose you have a symmetric combination, okay, then using the anti-commutator, you can reduce it to lesser number of gamma matrices. Okay. So therefore, the number of independent gamma matrices will have this property, which is that they will be completely antisymmetric in all their indices. Okay, and this is the list. Okay, and then of course to make this list not repetitive, we can impose conditions such as mu1 less than mu2 less than mu3 less than mu4. Okay, so that will ensure that there is no repetition. All right, and what we can see is that these gamma matrices, okay, and this symbol which I forgot to tell, so this symbol of antisymmetrization is done with weight 1. Okay, So the meaning of that is when you expand this anti-symmetrization, the number of terms you will get, you will divide by that number. Okay. For example, if you take gamma mu1, mu2, it is gamma mu1, gamma mu2 minus gamma mu2, gamma mu1 divided by 2. Okay. That is what it means to anti-symmetrize with wave 1. So this is the complete Clifford algebra. Okay. So now they also satisfy the relation, which I am not going to show, but it can be derived by using, sorry, that was not correct, ouch. Okay, where gamma B is the reverse set, okay, which is 1, sorry, one gamma mu 2 mu 1, gamma mu 3 mu 2 mu 1, and gamma mu 4 mu 3 mu 2 mu 1. Okay, where we still have the condition mu1 less than mu2 less than mu3 less than mu. Okay, so if you take these two sets, then you can show that the trace is 4 delta 8. In particular, if you take, for example, only one gamma matrix and the other is identity, then that will have 0 trace. Okay, so all these matrices are of 0 trace and their trace orthogonal to each other. So they are linearly independent. The way to show this is that if you take a particular gamma matrix, then you see that there is no natural invariant tensor that you can write down using Lorentz invariance. Okay, and the only case where you can write a natural invariant tensor is for this object, gamma mu1, mu2, mu3, mu4. Okay, and for that you can show that you can show by the fact that it can be defined as commutation of this matrix with some gamma matrix, and commutator has trace 0, so that also shows this is trace 0. So that completes that they are all traceless. Okay, so these matrices have this property, and yeah, I'm not going to derive it. Okay, but if there are any questions, I can take.
I think there's a question from Anirban.
Yeah.
So he's written it in the chat. He says, why is closed under multiplication important?
Oh, we are just trying to understand, there is an algebra structure, right? So we are just trying to understand if these gamma matrices span some space, okay? Because since they have an algebra structure, we would like to multiply them with to each other and construct an action, hopefully, right? Because these gamma matrices, they form a representation of the Lorentz algebra, which we will use to define some spinors, right, on which these gamma matrices act. And then using that, and when we have those spinors, and if you want to construct spinor bilinears and so on, then we would like to multiply these gamma matrices to each other, because that is the space where you have matrices which can act on the spinors. Okay, is that clear? Oh, okay.
Yeah, I think he's got it.
Yeah, but I think my sharing stopped, right?
Yeah, connect to
I think it's the Wi-Fi again.
Yeah. 1 second. Yeah. Okay. In fact, I am connected to the same Wi-Fi. I don't know what is happening. Okay, 1 second. Yeah, sorry for this.
Not a problem.
Yeah. Okay. So now we have these matrices, and yeah. So we.
Sorry, Subbu, we can't see your iPad screen yet.
Yeah. I have just begun speaking before I can. Yeah, just to save time. So I see. 1 second. Unable to connect to Zoom. Okay. HRI. Share screen.
But the screen is not visible. You can't see your screen.
Yeah, that's what I am not.
Subbu, one thing we can do is that since the number of participants is, yeah, it's coming now. Yeah.
Yeah. Okay. I don't know if it stopped sharing if I stop writing on it or something. Okay, I'll keep in mind. Okay. So now, can't help it. Okay. So, okay, now that we have defined these matrices and we have this property, right, and they span a space. Okay, so let us count the dimension of this space. Okay. So, of course, there are. Oh, okay. So I was asking if the answer was clear to Anirban.
Yeah, he said it's clear.
Okay, great. Yeah. So, of course, okay. So now we introduce this terminology R, where gamma R is gamma matrix of rank R. Okay. Where R is the number of these antisymmetric indices. Okay. So this is a terminology.
So does this R depends on dimension? Number of dimensions?
So okay, R is a variable, right? Like for example, this says R is equal to 0, this says R equal to 1, this says R equal to 2, okay? But of course, R can only go up to the number of dimensions. Okay? Because there is no antisymmetric tensor which is greater than the dimension of space-time, right? Of that space, because then some index will repeat and it will be 0, identically 0, okay? So here R goes from 0 to 4. Yeah.
Okay, so this is not the matrix rank. This is just the index that determines the gamma matrix.
Yeah. Right.
Yeah, Subbu, can I just point out something?
Yeah.
So yeah, naively, the rank R goes all the way to the dimension, but sometimes, for example, in dimension 10, there is a self-duality constraints. So the gamma 5 form is self-dual, and anything above 5 form, like 6 form is actually related to the 4 form, and 7 form is related to the 3 form.
Okay.
So
yeah,
they are not linearly independent. So in
so
10 dimensions, it actually goes to 0 to 5, for example.
Yeah. So okay. So no, I mean my point was that it can't go more than that space-time dimension. But like for example, if you consider odd dimensions, right? There also it is lesser than the number of dimensions, the rank. But my point is that that there is an obvious upper bound. Okay, like given a dimension, there will be more subtleties.
Yeah, exactly. That's
Right.
Yeah.
Right. That's
yeah. Okay. Yeah. So now, this 4CR. So given a rank R, there are 4CR number of those matrices, right? For example, there is one identity 4C1 gamma mu's and so on. Okay, and the rank goes from 0 to 4, right? Is this? So this is 2 to the power 4, which is 16, right? So therefore, the Clifford algebra spans the complete Clifford algebra spans the space of 4 cross 4 complex matrices. Okay. So these are the matrices. And
can you repeat? Subbu, can you repeat that whatever you just said? What is the counting argument?
Oh, the counting is that these indices are not equal to each other, right? Because these are completely antisymmetric, right?
Right.
So therefore, if you want to count how many of them there are, right? Then there are 4CR number of them. Like for example, 4C1 is 4 gamma mu and so on. And then you add them up, okay, from 0 to 4. Yeah. So that will give you the total number of these matrices. Yeah.
Right.
Okay. Yeah. Okay. So using this, using these matrices, we will now define a spinner. Okay, so let us define the Dirac spinner. Okay, as a complex, spinner, whereby spinner, okay, with 4 components. So maybe I should mention supersymmetry is done with 4 components as well as 2 components. Throughout these lectures, we will always use 2 components, and that is a line of questioning that I would encourage, like, not to go much on. Like, we will see how once we construct Majorana spinners, we can go to Weyl spinners, but at every step we will try to avoid doing that, because like these are completely like independent, vast subjects. So I'll restrict myself to 4 component spinners. Okay?
So one question.
Yeah.
In the this 16 that you get, okay,
yeah.
So what happens if there is that's not Hermitian representation?
Oh,
then also can you count it like this? Is there any counting argument?
Yeah. The counting.
This is for Hermitian, right?
No, the counting is the same.
Right. Okay.
Yeah. Okay. Because all these antisymmetric properties, they won't change, because the Clifford algebra is still the Clifford algebra. So, yeah. Okay. So lambda mean. So okay. So whenever we say a spinner, we mean this. Okay. Parameters of Lorentz transformations. Okay. So this is what we mean by this thing. And lambda dot gamma is a notation for lambda mu gamma. Okay. Is that clear? So this is a spinner. So now this is the Dirac spinner if we consider these as complex numbers. And now we can construct various bilinears using I psi dagger gamma 0 m psi. Okay, where m is summation A ma gamma, where gamma A are the matrices we defined earlier. Okay, so now of course given an m, we can find out MAs by using the trace orthogonality property. This way. Okay. So now we need to understand this object. Okay. So because ultimately we are interested in constructing Lorentz invariant actions. Okay. And what we will see that is that this has a transformation which is opposite to that of the spinner. Okay, so throughout these lectures, Dirac conjugate, we will keep writing as I psi dagger gamma 0, anticipating the fact that later we will define what is called as a Majorana conjugate. Okay, so Devanshu has a question. Okay, yeah.
Hi. So the variation of psi that you have defined, that is like that's an assumption, or you are getting it from somewhere?
Oh, I see. So we saw that this gamma mu nu by 2 is sigma mu nu, and that satisfies, that forms a representation of the Lorentz algebra. So I should have mentioned that. So because of that, we have, yeah.
Thank you.
Yeah. Okay. So now, yeah. So now, yeah.
Yeah, just a notation. What are the small NA?
So small what?
Small NA. This capital N you have defined as sum over A, NA gamma.
So these are coefficients, right? Because gamma, the capital gamma A's are like basis elements which span this 4x4 complex matrices, right? So you are writing M in terms of these basis elements. So there are
these are some coefficients. Okay.
Yeah.
Okay, thank you.
Yeah, sure. Okay. Yeah. So now Okay. So now let us go further. So probably till here, like in some language, people had already studied in Peskin, and we will come to that. Yeah. Okay. Yeah.
Sorry, quick question in the previous slide. So when you wrote the particular bilinear,
yeah.
So under a Lorentz transformation, this has to be covariant.
I did not completely show that there is the bilinear is Lorentz covariant. I mean, for example, this does not establish the fact that bilinear is Lorentz covariant because there is also M, right? So, but what I mean is that this is also necessary.
Okay.
For example, when M is identity, right? Then of course this means that I psi dagger gamma 0 psi is Lorentz covariant.
But is there an immediate way to see that that is true for the other gammas also?
Oh, I mean, okay. So what I mean is, so if M is like, let's say, if M is Lorentz covariant, okay, then you can show that the whole thing is Lorentz covariant. But we will see it later in for some other conjugation because they are of more interest to these lectures. So we will do that there. Yeah.
Okay.
Are there any more questions?
Yeah, I have a question. Maybe this is same as the last question. I'm slightly confused that this M seems to be from some, like, I mean, I guess the number of the gamma A, the A index kind of says what.
What
like,
representation?
It's a vector index, no? Like kind of. But then you seem to have an M which is a general vector which is added.
Yeah. It's like, I mean, ultimately in the Lagrangian, you will have something like this, right? For example, you might consider gamma A as gamma mu, right? But there will be some A mu, for example, some tensor which contracts with it, and that is M.
Yeah, but does it make sense to add the capital gammas with different R's?
Oh, definitely. Why not? I mean, they are matrices.
No, I just meant as a Lorentz.
I see. Okay, yeah. I mean, okay, yeah. So, right. So you won't. No. So for that, you just need that MA is also satisfying Lorentz under Lorentz transformation.
Oh, you mean these are just scalars that way? Okay, cool.
Yeah, MA gamma A is a scalar. Yeah. Okay, so this MA gamma A must be a scalar. That should be the requirement. Okay. Like for example, you can have A mu gamma mu plus, B mu nu gamma mu nu.
Yeah, thank you.
Yeah. Okay. So from now we will go into more details of the Clifford algebra, because what we are finally interested in is, can we restrict this complex spinor into lower number of components so that it must still transform under Lorentz transformations as a spinor. Okay. So the question is, can we construct a restriction, okay, which is invariant under Lorentz transformation? Okay, that is the question. And for that, we will need some properties of the Clifford algebra. So in every dimension, okay, and we will consider here only in 4 dimensions, okay, there exist matrices or matrix C, okay, which when you take the product with a gamma matrix, okay, gamma of rank R, it is either symmetric or antisymmetric. So if TR is -1, it is symmetric. If TR is +1, it is antisymmetric. Okay. So we will see an explicit example here. Okay. In 4D, we can have C1 is equal to sigma 1 tensor product sigma 2. C2 is equal to sigma 2 tensor products. Okay. So these are 2 matrices, which, so in product representation, if you multiply these matrices with the gamma matrices, okay, of any rank, then it is either symmetric or antisymmetric. Okay. So I am not going to prove in these lectures that I mean how to derive these matrices and so. Okay, we will consider them as given. Okay, but for C1, we will have these values. T0 is 1, T1 is 1, T2 is -1, T3 is -1. Okay, we don't need to by heart this. Someone will give it to us. I mean, it's there in many books. Oh, maybe I should mention an important reference for all these lectures is Supergravity by Friedman and Van Proyen, which is a book which teaches you to calculate. Okay, and there are also other references. I mean, there are various other references. There is a recent book by Van Proyen and Loria. Okay, and for part of the lectures, we will also use the papers that I listed. There is a review by Mohab, which is called Black Hole Entropy, Special Geometry and Strings. And there is also this paper by Butter et al. Yeah. So these are the C matrices, and these are called as charge conjugation matrices. And they have these properties, which is if you know T0, T1, you know all the rest. Okay, T4 is 1. So it goes like this. If T0 is 1, T2 is -1, T4 is 1. If T1 is 1, T3 is -1. Okay, the sign alternates. Okay, when you mod 2 okay, for the land. So you just need to know what is T0 and what is T1. So you can derive it for a specific dimension, but we won't do it. Okay, but it is there in Friedman Van Proyen in chapter 3. Okay, are there any questions at this point? Okay, let me continue. Okay, so now of course we gave it in one representation. You can verify that in another Hermitian representation, C goes to C prime, which is S star, S star, okay, where gamma prime R is S, gamma R star. Okay. Oh, sorry, I hooked up. Okay. This is C. Okay. So, I mean, of course, to define Majorana spinors, one need not really go through this route. One can define in a definite representation in an easier way, but I am just going to do in a language which will be easier to make representation independent. Okay. Okay. So far it's just mathematics. We are just saying that there are matrices like this which have some property. So now let us define some useful concepts. First is Majorana conjugation. Okay, and Majorana conjugation can be defined for any spinor. Okay, it's nothing to do with the Majorana spinor. Okay, so given a spinor, you can define a conjugation. It's called psi transpose C. Okay, and this transforms as follows. So Majorana conjugate, okay, transforms just like I psi dagger gamma 0. Okay, that is one thing that I want you to note. Okay, and basically once we use Majorana, once we start using Majorana spinors, this conjugation becomes extremely convenient. Okay, which is why we are studying this. Okay? And it transforms in this way. This can be checked. Where the one thing you will need to use is that C gamma mu transpose is whatever, you know, minus T2. Okay, this you will need to use. Okay, and C transpose is minus T0 C. Okay, and T0 T2 is minus 1 because the signs alternate. Okay. So if you use these three, then you can show that it transforms in this. Okay, and I leave it as an exercise. Are there any questions?
Yeah, Subbu, I have a question. So the notation that you'll be using now, the first line, psi bar equals gamma transpose C. That's your notation for a Majorana conjugate.
Yeah. Yes.
And if you will you at any point need to use a notation for the Dirac conjugation, or will you always write minus I psi?
No. I'll always write I psi dagger comma for Dirac conjugate.
Okay, thanks.
Yeah. Okay. So now what we will do is that we will use some useful properties of Majorana conjugate, okay, bilinear constructed out of Majorana conjugation, so that like once we go to supergravity, we can use these properties to do various manipulations. Okay, so the properties to follow are some of the most important properties of spinors that we will need, but to derive these properties, we will need some relations. We will need some notations, which is sometimes we need to write fermion indices explicitly. So far we have suppressed them, so we will write fermion indices. And another thing is that I have not so far mentioned is that we are doing classical supergravity, but in a Lagrangian language. So fermions are Grassmann numbers. Okay, so the anti-fermion. Okay, so these two things we will use now. Okay, so first we will give some notation. So spinor psi we will write as psi lower alpha. Okay, and alpha runs from 1 to 4. Okay, and psi bar we will write as psi bar alpha, which is C alpha beta psi beta. Okay, this is the definition of psi bar alpha. So it's basically a way of writing psi bar is psi transpose C. Okay, so okay, and okay, so here the way it is written, C alpha beta are components of C transpose. Okay, because what we are doing is we are just doing something like this. Okay, in this expression. Okay, so therefore C alpha beta are components of C transpose. Okay, so the indices become a bit confusing in what is to follow, but we won't use it as much except deriving the Fier's identity. So we will see if there are any confusions. Okay, so now we can define a C lower alpha beta can be defined such that psi alpha to psi bar beta C beta. Okay, so using this and of course using the fact that like psi for psi bar you can again substitute the first relation. Okay, you can substitute 1 in 2, then you get the relation C alpha beta C rho beta is equal to delta alpha rho. And this can be written as C alpha beta C beta rho transpose. So in the end, so C alpha beta are components of C transpose, and it's a unitary matrix. Okay, that I should have specified. So if you look at C's here, okay, these are unitary matrices because polymatrices are unitary. Okay, and this feature is always true that it's a unitary matrix. Okay. So C's are unitary, therefore C alpha beta are components of C inverse. Okay.
Is the view paused?
Yeah, I think there's some problem with the connection.
Yeah, I think so.
Subbu, are you there? I can see him in the participant list.
Yeah, he's still logged in, but something happened. You call.
Biswajit, if you are there, can you just check up on Subbu? Anyone from the HRI actually can.
Arnav is there, no?
No, I am at home actually.
Oh, okay.
I guess the HRI internet is down. Maybe I should try calling Subbu.
Yeah, I'm already calling.
Oh, okay.
I can see Abhishek is there. Abhishek, can you hear me?
Yeah.
Hi, Subbu.
मैं अभी करूँगा एक सेकंड. No, that's because Abhishek is near me. 1 second. Okay, yeah. Okay, now.
Yeah, now probably Subbu is back.
Okay, now I am back. Yeah, I'm sorry. Yeah.
Okay, Subbu, you still have the co-host, right? Yeah.
Yeah. That's good. Yeah. Okay. Were there any questions about that?
Maybe I have a question.
Okay.
Yeah.
What restricts the value of T0 and T1 to be 0 and 1 that you were writing down?
Oh, 1 and minus 1, right?
Sorry, 1 and minus 1, yeah.
Oh, okay. So, I mean, it's not, okay. So basically the claim is that there exists a C such that when you multiply with gamma matrix, it is either symmetric or antisymmetric, this combination C gamma, okay?
Okay.
So that is what tells you that either it is symmetric or antisymmetric, and TR is used to capture that.
Okay.
Right? I mean, if TR is, let's say, -1, that means this is +1. So then C gamma R is symmetric. So the claim is that such a matrix always exists. Okay? And to avoid going into it like in a lot of detail, so I have just given examples in 4 dimensions. So these are the only 2 matrices up to the basis 10 that I gave. Given a definite representation, these are the only 2 matrices which satisfy this.
Okay, and the claim is that once T0 and T1 are known, you can determine T2, T3, T4.
Yeah. That can be derived. But also, since I have given you examples, you can just evaluate it. You can just take, in the product representation, you can just work out gamma matrix of rank R of any one of them, and then just multiply this matrix and see what is TR.
Oh, okay, thanks.
Yeah. So you have all the tools except that I have not derived it in the most general way. Okay, but you can work out all these values on your own. Are there any other questions?
I have a request.
Yeah.
Can you just write the explicit indices on the expression for bilinears?
Okay, I will write when it is relevant. Yeah.
Okay.
Because because otherwise, like, things will become extremely cluttered. Yeah.
Yeah, sure. Right.
Okay. Yeah.
Subbu?
Yeah.
I think your screen had paused before the second half of the slides. So maybe just for clarification, you can just repeat some of that.
Oh, I see. Okay, sorry. Yeah. So okay. So we represent the matrix psi as psi alpha, psi bar alpha as C upper alpha beta psi beta. Okay. And that is a way of writing psi bar as C transpose psi whole transpose. So this tells us that the C alpha beta are components of C transpose. Okay. Now we can define another matrix called C lower alpha beta, such that psi alpha is psi bar beta C beta alpha. Okay. And when you substitute equation 1 inside equation 2, you get this relation. Okay. And one thing which I had forgotten to tell, which I told, but maybe I was frozen, which is that these C matrices are unitary matrices. Okay. Like, for example, in this slide, the examples I gave are unitary matrices because polymatrices are unitary. Okay. So using unitarity, we can see that the C lower alpha beta are complex conjugates of C upper alpha beta. Okay. So, and what I was saying is that it might be a bit confusing, but I don't need it in great detail. So that, but I have worked it out in detail in the notes. So I just went fast here. But if there are questions, I can take them.
One more quick question. Is there a way of raising and lowering these indices on C?
On C?
No,
I mean, C is the matrix that raises and lowers indices.
I see. Okay.
And of course, I mean, this is like the metric, right? In the sense that if you look at it this way, like suppose this C alpha beta, right? One index was lowered by this C rho beta. So it's like delta alpha. If you use another C, then it becomes the lower C.
Right. So the C is to be understood as a metric in this.
Yeah.
So there was a choice in the C's when you. I mean, there were two choices in the C's.
Yeah.
Does that play a role? I mean, the fact that you have these two choices.
Yeah. Only one of them will be compatible with the definition of Majorana spinors. So I'll come to that. Yeah.
I see. Okay.
Yeah. Okay.
Sorry, Subbu, I just have one comment.
Yeah.
So this is usually the point in the supergravity lecture notes or books where I stop reading because the indices and the notation is just like absolutely terrifying to me.
Yeah.
But I just want to say to everybody else in the audience that because it's not the usual suspects are asking questions, so please feel free to kind of get any of these doubts clarified because like this is a good point to do so.
Yeah.
I have a question. So I understand that we are constructing the algebra and understanding the behavior and all of these matrices, but can you say where we are headed to?
Yeah. So what I was saying is that we need a Lorentz invariant. We need a Lorentz invariant condition where. Oh, okay. Can you still hear me?
Yes.
Okay. Yeah. So we need a Lorentz invariant condition where to define a spinor of lesser dimension. And the reason for doing that is that if we want to construct the simplest supergravity theory, okay, then it will have the simplest spinor in that dimension. Okay. So in this lecture, we are trying to construct the simplest spinor in 4 dimensions. Okay. So for that, we need a Lorentz invariant condition. And we define this Majorana conjugation, which transforms the same way as I psi dagger gamma 0. Okay. So later we will see that this Majorana conjugate being equal to Dirac conjugate is in fact the Majorana condition. And since they both transform the same way under Lorentz transformations, the condition is also Lorentz invariant.
Okay, and this generalizes to higher dimensions also?
Yeah.
Like right now we're focused on 4D.
Yes. Yeah, this C matrix, the language is so that it generalizes to higher dimensions. Yes.
Okay, thanks.
Okay, Devanshu has a question. Devanshu, go ahead.
Yeah. I'm trying to fix my screen, but yeah, please ask. Yeah.
Subbu, I have 2 questions. First is, okay, not directly related. Since you are anyway working in 4D, my question is the number of C's. So you have given an example in 4D product representation. We got 2 C's. My first question is, how is the number of C's decided?
Yeah.
Or is there a relation with dimension? Second is the number of C representation dependent? If I used a different representation, would I have got 3 C's? I doubt that's...
No, right. So that is, right. Yeah. So in any even dimensions, you will have 2 C's. Okay. And in
any even dimension.
Yeah. So, and in odd dimensions, you will have 1. And it can be derived that because a C comes with a specific set of TRs. Okay. And you can derive what are the possible TRs in that dimension. Okay. Oh, okay. Yeah, okay. So this will have some delay, I guess, but yeah. Okay. Yeah.
I mean, I just temporarily shared it until you fix it.
Oh, but I can't fix it until,
I see. Okay, then let me...
Yeah.
So while you are trying, there is another question.
Yeah, sure.
In the chat, probably if you want to ask, Gravity, if you want to ask, you can just directly ask. Or this question, I will just read it out. This question is, how is the product representation related to the bispinner notation?
Oh, okay. I mean, product representation, I see. Okay. I don't think the product representation is related to the bispinner notation. There is something which we will see later, which is called as the Weyl representation. That will be related to bispinner notation.
Subbu, your iPad is still connected to the Wi-Fi, right?
Yeah.
Maybe
okay.
The simplest thing to do is that you log into Zoom through your iPad as well. And I will give your iPad hosting right and you share directly from iPad.
Yeah, that would be great. Yeah, please. Okay, so I will join in Zoom. Okay. This person has Slack.
1,000 unread messages. Okay, that's irritates me, but okay.
Sorry?
So I can read you the meeting ID and password. Don't worry about it. You just go to Zoom.
Yeah, actually, Subbu, maybe it would be a good idea for you to not share screen during this.
I see. I mean, it's not my iPad, so I have.
Oh, okay, all right. As long as it's someone else's information.
Okay, go to join.
Yeah.
898.
898.
336.
336.
2915.
Okay. Join.
Great. Now some Russian bot is going to log on to this.
1043.
Okay, now it also started mirroring my screen, right? 1043. Okay.
11.
11. Oh, sorry, what?
104311. And stop sharing from your Mac and start sharing.
Yeah, let me in though. Okay.
Let him in the room. No, what's your problem?
He's already in and the co-host.
Sorry, I'm just messing around.
Okay.
Yeah, so now just screen share from your iPad and you can keep your iPad muted and speak from your Mac.
Okay, 1 second. I've never done it, so I'm extremely confused.
Yeah, no problem.
Share screen. How do I just share the screen? With photos, is it? I have to record it with some app, it seems. Okay, Zoom. Okay.
Yeah.
Okay.
That's great.
Yeah. Okay. Yeah. Okay. So am I audible twice now or something?
No, it's perfect.
Okay, great. Okay. So should I switch off my video because I may not be visible anymore, right?
You are visible from your Mac.
Okay. Okay. Great.
Just go on. Just go on.
Okay. Sure. Yeah. Okay. So this is not related to, the product representation is not related to bispinner notation, and we will come to the point where it is related to bispinner notation. Okay. Yeah. So now we will derive what is called as a Marana-Flip relation. So now this Marana-Flip relation is basically if you have a bilinear which is psi bar gamma r chi, okay, where psi and chi are two spinors. Okay, how is it related to chi bar? Sorry for the handwriting. Chi bar gamma r psi. Okay, if there is any relation. Okay, and we will see that there is. Okay, so firstly note that this is just a number, right? Psi bar gamma r chi, okay, because all the matrices have been made numbers by taking rows and columns, okay? And therefore, if we take this bilinear, then it is equal to its transpose, okay? Now, this psi bar was psi transpose C. Okay. So, if you take the transpose now, okay, so now I will use a notation which is sort of maybe a bit puzzling, but okay, this is often used, which is that if we have two Grassmann numbers, theta.
I have a question.
Okay.
So this transposing, like, aren't these guys Grassmann odd, psi bar and chi?
Yeah, yeah.
So shouldn't I be like more careful, or shouldn't I put an extra minus sign or something?
When I actually take the transpose of individual terms, right, then I have to be careful, which is what I'm trying to do now. But if you take the whole bilinear, it's just a complex number. So if you take its transpose.
Okay, you haven't like really, okay.
Right, because I have not manipulated the things inside, which I'll do as a next step. So then we will do that. Yeah.
Okay, sure.
Okay. So for Grassmann numbers, if we have two Grassmann numbers, there are various conventions, and I will use this one. Where if you take complex conjugate of products of Grassmann numbers, complex conjugation interchanges the order, okay? And if you do the transpose interchanges the order with a minus sign, okay? And Hermitian conjugation is just this. Okay. There are various possibilities, okay, but we will use this this convention, okay. And so when we do this step, okay, as Akhil said, we will be careful and we will write it as minus chi transpose C gamma r psi, okay. Okay, so C gamma r transpose, okay. So these thetas are to be thought of as, you know, like general Grassmann numbers. So we have considered C gamma r chi as a Grassmann number and psi transpose as another Grassmann number, and we have taken the transpose, okay. And because these are Grassmann numbers, there is a minus sign, and C gamma r transpose is minus TR C gamma r. So we will get TR chi transpose C gamma r psi. So we will have TR chi bar. Okay, so psi bar gamma r chi is TR chi bar gamma r psi. Okay. And the usefulness, I mean, of course, like by now, like people might be thinking, why do we have to go through all this? Okay. So the usefulness of this is that when you do supergravity, there are various number of fermions in each of your expressions, and it is useful to bring fermions together so that you can collect various terms. Okay. So this relation, Marana-Philip relation, what it does is that it flips which spinner is barred. Okay. And then there is another relation called Freer's identity, which will allow you to change the barred one with the normal spinner in some other bilinear. Okay. So you can group various spinners using these two relations, and they're extremely important in supersymmetry. Are there any questions?
Yes.
Yeah, I have a question.
Yeah.
Why does this Hermitian conjugate doesn't have this minus sign?
Okay, so if you
in
fix
Grassmann product.
Yeah, if you fix like two of the signs, the third sign is fixed by itself. So, like if you fix the first two, right? Theta 1, theta 2 star, as theta 2 star, theta 1 star. And if you fix the transpose, this thing also, convention also, then the Hermitian conjugation is just complex conjugate transpose. So that will get fixed on its own.
So I have a question on that. Like, theta 1 and theta 2 here are Grassmann numbers, or are the matrices or some vectors?
Okay, these are okay. So these are Grassmann. Okay. So these are Grassmann matrices, but with so I'm abstaining myself from calling them, like psi bar, because the upper index we gave for psi bar alpha, right?
Right.
So that is why I'm not calling like one of them, let's say upper alpha, because that means something else. For example, here psi transpose, right? We are taking a transpose of that, but psi transpose had no index in our notation, right? We only had a notation for psi and for psi bar. Okay.
Correct.
But yeah, I mean, these have some indices, and these are more general objects, and these objects are mapped to those objects.
I see. So again, coming back to the theta 1, theta 2, this thing, for example, I mean, what I'm a bit confused is complex conjugation seems to rearrange the order.
Yeah.
And if they're numbers, and transpose also seems to rearrange the order.
But with a minus sign, yeah.
With the minus sign. So that, I mean, if they're numbers as opposed to vectors, I find that a bit confusing.
Yeah. I mean, they have some indices, yeah. I
Okay.
mean, what I mean is that you can probably call it A and B, upper A, lower B or something, but for the lack of notation, I'm not doing that.
I see. And if they are some extended object, like some vector or matrix, why is complex conjugation flipping the order?
Oh, I mean, this is the Grassmann nature of them that makes them flip the order, the complex conjugation. But I mean, as far as I have seen, like this is like, you can also make it not switch the order, then the conventions will change.
Okay.
So people usually prefer this Hermitian conjugation relation, okay? Because we will use Hermitian conjugation more than the other relations, like in supersymmetry, right? Because like once we construct everything, these two things we might as well forget, like the complex conjugation and transpose, okay?
Right.
So therefore, people use like Hermitian conjugation more, so they want this sign. So they define the other two accordingly. Like some people don't want a minus sign here, okay?
I see. Okay.
Then then this thing will not change orders and so on.
Okay. I see. Okay.
Yeah. In the appendix of Van Proyen, there are like these conventions done in a general way, like some alpha beta numbers they have given, and if it is +1, it is one convention. If it is -1, it is another convention, and so on.
I see. Okay.
I just have a comment about Anish's question.
Yeah.
So I think that, I mean, just from a purely mathematical standpoint, one is sort of asking the following question. I think so. Please correct me if I'm wrong about this. But you start off with Grassmann numbers, and they have this sort of anti-commutation property. Now you say if you want to define a conjugation, how does one go about defining a conjugation in a consistent way? And similarly, if you want to define transposition, how do you define transposition in a consistent way? So I think the sort of choices of signs that Subbu is talking about essentially come from what are the consistent assignments of those phases, essentially, that are compatible with some nice properties that you want the final structure to have. So yeah, that was the comment.
That's a very nice way of putting it, I think. Yeah, that is true. Yeah. So these are like new kind of objects, and people use various conventions basically to, basically according to their convenience. But ultimately, these are new objects, and yeah.
So Subbu, Advait has a comment in the chat that maybe you'd like to address. He says, I think it's time to start writing down all indices. So maybe you want to say something about that?
No, I mean, okay. So with my experience in supergravity, I think if we write all indices, it will become extremely messy. So I will prefer not to write indices.
Yeah, I will like to second Subbu, and I will say that there is never a good time to write all indices in supergravity.
Yeah, I mean, okay, like for example, okay, like Marana flip relation probably could be made more, okay, yeah, Advait, you can speak, yeah.
Oh, sorry. No, I just meant that maybe once you can write the indices so that we can keep in mind. You not start. I'm not saying you start writing indices, but once if you write it, then you don't have to repeat it again.
Yeah. Yeah. Okay. So first of all, see, when we did this derivation, right? Like when we did the Marana flip relation, it was inconvenient to use the indices because we gave index to psi transpose C. Okay.
Mm-hmm.
So it becomes inconvenient to take the transpose of psi individually, like of psi transpose individually. Okay.
I see.
But of course, once you write it, then I can write this. I mean, once we write the final answer, chi beta. Okay. I mean, you can write psi bar alpha also, but people suppress it usually. And you can write chi bar alpha, r alpha beta psi. Okay, this is the final answer.
I see. Yeah. Thanks. Sorry.
Okay. Sure.
Yeah, I also have one more comment about this, like whether to write indices or not business. So I have some experience doing some computations like this. And one of the things that I have found is that from a computer algebra standpoint, and maybe Subramanya can also sort of chime in on this because I know he has some experience with this, but like teaching a computer to recognize strings and manipulate the strings in a particular way, for example, with this Majorana flip identity, I find it a lot easier to do it without the indices than with the indices. So from a strictly computational standpoint, also, even if you're not doing it with pen and paper, I think using the sort of compact notation is more profitable.
I see. Okay, I've never done it with computers, but I guess Madhu is trying to say that for both hand calculations and for computers, suppressing indices is useful. But sure, for the next relation that we are going to write, which is the Fier's identity, we will definitely use the indices. Okay. And then we will also see how to suppress the indices. Okay. So the next object is Fier's identity. So what we had seen earlier, so let me write now in indices. Okay. M alpha beta was summation A, M A, gamma A alpha beta. Okay. So this was our general 4x4 matrix. Okay. So now consider a set of such matrices. Let's say M mu nu, which are spectator indices, and alpha beta, and we will have delta alpha nu, delta mu beta. So let us take this matrix, okay? And the matrix indices here are alpha and beta. Okay? Mu and nu just indicates that we are taking a whole collection of these matrices. Okay? So then we had this relation, which is that MA is 1/4 trace gamma AM. Okay, of course, this also we can write in indices alpha beta M beta alpha. Okay, so if you use this relation, okay, if you use this matrix, okay, then you can show that MA mu nu are spectator indices and MA is a spectator, right? So MA will have those indices. Okay, MA mu nu is 1/4. Okay, and I leave it as an exercise to just substitute this matrix here and prove this. Okay, it's easy. It's just one index makes alpha. Okay, I should probably write. Yeah, I mean basically. One index makes alpha mu and beta mu, but I just changed the dummy variable. Is that okay?
Subbu, one question. So this is, I mean, this relies on the fact that you are in 4 dimensions. Or is this statement is true irrespective of dimension?
Okay, so in all even dimensions, this will be 2 to the power d by 2. Is 4 factor. Okay. Right, so in odd dimensions, there is the subtlety of like gamma matrices being like the gamma matrices I listed are not linearly independent, and for some reason Subramanya says in 10 dimensions also that is true. So yeah, but I mean, but like whenever these gamma matrices are useful, whatever I have said, okay, then this is the only change.
Okay.
Okay.
Subbu?
Yeah.
Hi. So
Hi.
I didn't understand the spectator indices. What do you mean by spectator indices here? Like I thought the left hand side for the first equation that you wrote, M is MA gamma A with the spinor indices.
I mean something like this.
Okay.
Okay. In the sense that M could have many other indices, but we are only addressing alpha and beta through this relation.
I see. Okay. So the A's are the space-time indices. Mu nu could be any other index for.
Mu nu are actually spinor indices like alpha, beta, mu nu. All these are spinor indices. Yeah, maybe I should not have used mu nu, but we will suppress it eventually. But
Okay.
All these are spinor indices, but these are spectator indices. Okay.
Okay. Thanks.
Yeah. Okay. So now using this, we can write delta alpha nu, delta mu beta as 1/4 summation A gamma A mu nu gamma. Okay. So basically we just substituted this answer back here. Okay. So why is this useful, you might ask? And the usefulness comes from the fact that we could do, for example, psi bar alpha, chi beta, delta alpha nu, delta mu beta, okay, which is just multiplying this thing here. And of course, this is psi bar nu, chi mu, okay. And like if I keep it like this, then I can't suppress the indices, right? Because this will look like a bilinear. So to avoid that, I will do this chi mu psi bar, okay, because these are Grassmann numbers. Okay. So if we take this object, right, then this is equal to, I hope this is visible, 1/4 summation A gamma A mu nu psi bar gamma A chi. Is that okay? Because what is happening? Like when you multiply with this on the RHS, right? Psi bar goes with this alpha, chi goes with this beta, right? So they form this bilinear, psi bar gamma A chi. You can write them with indices if you want it. Psi bar upper alpha, gamma A alpha beta, chi lower beta. Okay. But if you consider this object, which is chi psi bar, okay, that can be made into some operators times psi bar gamma A chi. Okay. So this is called as Freer's identity or Freer's rearrangement. Okay. And this is useful because what can happen if we have some number of spinors, then what can happen is that suppose you have some psi bar 1 m chi 1 psi bar 2 m chi 2. Okay, you might have many maybe m prime. You might have many terms, right, like in supersymmetry which you are trying to cancel. Okay, and for that purpose you might be organizing in such a way that chi 1 and chi 2 have to come together. Okay, so what you can do is using Marana flip relation. Okay, you can flip chi 2 here, okay, by saying, suppose this was some gamma matrix of rank R, then you will have, okay, maybe I should have written it that way. Sorry. This is gamma R, this is like, let's say gamma Q. So then we will have psi bar 1, gamma R chi 1, and T Q chi bar 2, gamma Q psi 2, where I have used Maharana flip. Okay. Now, how do we bring chi 1 and chi 2 into one bilinear? We use Freer's identity, okay, which we defined here. Okay. So if we have, let's say, chi 1, chi 2 bar, then we can make chi 1, chi 2 come to a single bilinear by using this. Okay. Right. So we can use the Freer's identity here. Is that clear? So this is why these two relations are extremely useful, and we will later see how this is useful to establish, let's say, Soucy invariance in super-Yang means. Are there any questions?
Just a comment.
Yeah.
I don't know if this. I don't know if you mentioned this before, but so the gamma q in principle can run over from 1 to 4 in 4 dimensions. But in more than 4 dimensions, the q can run higher than 4. And if the so then the TRs, the way to find the higher dimension, that is you sort of, the T's are modulo 4.
Yeah, I mean, basically what I said is like T's alternate sign for mod 2. Okay.
Okay.
Like TR is minus TR plus 2. Okay. And TR is equal to TR plus 4 is like a consequence of that.
I see.
I know that in Friedman they only say it's mod 4, but you can also derive that it's the alternate sign. Yeah. So if you know T0, T1, you know everything. So that's why all the discussions usually are about the T0, T1.
I see. Okay. Thanks.
Okay. Are there any more questions?
Subbu, just a request. Can you write the phase identity for chi1, chi2 bar separately? Like,
yeah. Sure. Okay. So chi1, chi2 bar is minus 1 over 4 summation A chi2 bar gamma A chi1. Okay. For those of you who want to write the indices, chi1 alpha, chi1 beta, chi1 2. Is that clear? So gamma is the operator which carries this alpha and beta index. Okay, and this is a bilinear. Okay, this one. Okay, that is great. Okay, so I get 15 extra minutes. Is that okay? I mean,
yeah. Please go on.
Okay, sure. Okay. So, okay, are there any questions about the Fier's rearrangement and why it is useful? This, I mean, did people understand this? It's quite important. So, if you want to ask questions, please feel free to. Okay.
Yeah. Sorry.
Just
in anticipation, what do we gain by doing this? Like this rearrangement, what does it buy us in, let's say, constructing Lorentz invariant terms in final Lagrangian?
Okay, yeah. So these rearrangements are more important for Soucy invariance of the final Lagrangian. Okay. So what happens is that okay, let's say for example in this term, right, psi bar 1 gamma r chi1, psi bar 2 gamma q chi2. Okay. Suppose this chi was the same spinner. Okay. Let's say chi1 and chi2 is equal to chi. Okay. All right.
Yeah.
So now you would like to bring chi in the same bilinear. Okay. Because then chi bar something chi might have some nice properties. Okay. For example, let's take chi bar gamma nu chi. Right. This has the property by by Marana-Flip relation, right? If you take chi bar gamma mu nu chi, this is T2 chi bar gamma mu nu chi, right? Where I took this chi here, this chi here. Okay.
Yeah.
Now there is a C for which T2 is minus 1. Okay. That, I mean, in 4 dimensions, both the T2s are minus 1. You can see. Okay. So it is. So chi bar gamma mu. Oh, okay. Why did I make this gamma mu? Sorry. Normal gamma mu. Okay. Gamma of secondary. So psi bar gamma mu nu chi is minus of itself, so it is 0.
Yeah.
Okay. So it may not be obvious that these contributions are 0 if you look at this thing. But if you bring the similar spinors together, then you can see that it simplifies. Okay?
I see.
And this is useful.
Okay, yeah, thanks.
Okay, so basically the advantage of superspace is that it avoids the usage of this Marana flip and Sears identity. Okay, these are seen as very tedious, and they are indeed very tedious. Okay, so so that's but well, I mean, like superspace is restricted for its own reasons because the description is not available for various theories, and for component techniques, these two are, although tedious, useful relations.
Nice. Okay, thanks.
Okay. So now I will do something which is familiar to almost everyone here, which is you can define a matrix gamma phi. Okay. So, okay, maybe I have a question to Subramanya after this. Okay, let me see. So gamma phi square is 1. Okay. So we know that gamma phi can be defined this way, and it squares to 1, and it is Hermitian. Okay. So this is called as the chiral gamma matrix. Okay. And it is related to the highest rank gamma matrix in this way. Where throughout these lectures, whenever I use Levi-Civita tensor, okay, I will always use it with an I factor, imaginary I absorbed, okay? Because then the contraction of Levi-Civita tensors become easy. Okay? So for example, if you have epsilon mu nu rho sigma, epsilon mu nu alpha beta, then this will just become 1 over 2 delta rho alpha delta sigma beta. Rho beta. Let me check if it is 1 over 2 is correct.
You mean you're going to use purely complex Levi-Civita?
One second. 2 factorial. Yeah, okay. This factor, I don't know. It's usually p factorial and n minus p factorial. So I guess this should be 2 instead of this. Yeah. Okay. So Levi-Civitas are complex. What happens is that if you don't define it with an imaginary I, then there is an additional minus sign here. Okay, and this we don't want. So we have absorbed an I, imaginary I.
So your epsilon 0, 1, 2, 3 is plus I. Is that what you're saying?
Yeah.
Thanks.
Okay. So now,
just to be careful, the epsilon 0, 1, 2, 3 lowered or upper one, which is I?
I think the upper one is I, but it won't be relevant for these lectures. I mean, this convention. Yeah. But you can take the upper one to be I. Okay. So now, so now trace of this is 0, right? Which we saw earlier because it's a member of the complete Clifford algebra. Therefore, trace of gamma phi is also 0. Okay? And you, with the product representation, you can explicitly verify this also. Okay. Now, gamma phi square is 1 and trace of gamma phi is 0. That means there exists a representation. Okay. There is a representation in which gamma phi takes this form. Okay. Well, these are 2 cross 2 identity. Okay. And you can show by the fact that this gamma phi, you can show it anti-commutes with all the gamma matrices, all the first rank gamma matrices. Okay. And it commutes with the second rank and so on, anti-commutes with the third rank. So using that, you can show that gamma mu in this representation is 0, sigma mu, sigma bar mu, 0, where sigma mu is also equal to sigma bar mu, which is 1, 2, comma Pauli matrices. Okay. And this representation is called as the Weyl representation. Okay, and this representation is important to define chiral spinors. Okay, and which I will just do it right away, and then we can take questions. So we can define these projections. PL is half 1 minus gamma phi, and PR is half plus gamma phi. You can check that it satisfies all the properties of projection matrices. Okay, PL square is PL, PR square is PR, PL plus PR is identity, PL PR is 0. Okay, so these are orthogonal projectors. So, and also further, you can show that there is an alternate basis of gamma matrices. So this is not exactly related to the point above, but anyway, when we take these projections, this basis becomes useful, which is 1 gamma mu 1. Subramanya, is this the kind you were saying in 10 dimensions? This kind of basis?
No, not really. So in 10 dimensions, what I was saying is that without using this gamma 5 or gamma 10 in that particular dimension, even then, so basically in 10 dimensions, what happens is that, you have this Hodge duality relations where you can map this D form to D minus P form. But in 10 dimensions, the Hodge dualities are actually equalities. So anything higher than the 5 forms, the 6 forms is actually can be written in terms of 4 forms. The 7 form can be written in terms of 3 form, and so on and so forth. So even prior to constructing the gamma 10, the number of bases is actually exhaust at gamma 5, remembering that the gamma 5 is self-dual.
I see. Okay, that I find very surprising. Okay, let's see. Maybe I can discuss with you later, because like here also, the way I have done this basis transformations, okay, it is in some sense related to Hodge duality, in the sense that you take, Ravitej, I'll just take your question in a second. So basically you take, let's say gamma mu1, mu2, mu3, and then you apply epsilon mu1, mu2, mu3, mu4. And this in fact gives you gamma phi, gamma mu1, proportional to gamma phi, gamma. So maybe we can discuss later. Okay.
Just a question on Shubhranil's comment.
Yeah.
The Hodge duality is an equality, that the Hodge duality is equality in 10 dimension. Is it true only for gamma matrices or all matrices?
It's definitely true for the gamma matrices. I don't think it's supposed to be true for all forms.
Okay, I'm very surprised because this kind of relation, right? This gamma phi, gamma mu1 is like true in all even dimensions. Like in even dimensions, whenever you take like Levi-Civita contraction with gamma matrices and keep some index free, you will get like the Hodge dual type of gamma matrix times gamma 5, the highest rank matrix. And in 11 dimensions, I can understand that Hodge dual will be equal. In all odd dimensions, that is true, what you are saying. So I am puzzled that.
No, in 10 dimensions, there is actually a very simple physical way of saying that why it should be true. So for example, in 10 dimension, there is this type 2b supergravity, which in the bosonic sector has a self-dual form field. Okay. So if you have to have supersymmetry, you have to write down some fermionic bilinears, which transforms, under the self-duality transformation, it should transform back to itself. So there has to be some gamma matrix with exactly the same number of indices as the form field, which is the 5 form field. So the gamma 5 form has to be self-dual. And the fact that the gamma 5 form is self-dual, you can show that by consistency, it means that all the P forms should be dual to the D minus P forms as an equality.
Are you doing it in like, let's say on Weyl spinors?
These are 16 cross 16 in 10 dimensions. Yeah.
Yeah. So see, in Weyl spinors, you may not see it, this gamma phi, because what happens is that, for example, if this gamma, let's say gamma mu1, mu2 in 4 dimensions, okay, if it acts on, let's say, left-handed chirality spinor, okay, then this is anti-self-dual. And when you have Weyl spinors, that always happens, that this is either left chiral or right chiral. If it's right chiral, it is self-dual. So yeah, I mean, it might, so depending on the spinners you take, there can be simplifications. Yeah.
No, it's not. It's much more. It's bigger than that actually. So the self-duality, anti-self-duality that I'm talking about is that of the bosonic form field itself. So for real bosonic form fields, you can have self-duality conditions only in 2, 6, 10. So 4n plus 2. So this is something that you will not see in 4 dimensions. So 4 dimensions
Yeah,
you will never have
But Subramanya, I can just I can just derive this in any even dimension. So maybe we can discuss later. I mean, because all these like other fields that you're mentioning are outside the Clifford algebra structure. Okay, so what I am saying is that if you have some other fields, okay, then it might be true that you take only certain combinations and they work out for those fields.
No. So the other fields that I said is just to give you a simple physical motivation. That
I think we should really discuss it later. I mean, this is also a exercise in Van Proen that whenever this is true, there is the highest rank gamma matrix. So we can discuss it later. Okay. So Raviteja had a question.
Yeah, I think it's covered pretty much in your discussion. Yeah.
Oh, I see. Okay.
I'll message privately if I have any doubts.
Okay, sure. Yeah. We can also continue on Slack this discussion. I can point to the exercise on Van Proen and we can see if that is true. Okay. So let me continue. So these are an alternate basis of gamma matrices. Okay. And this alternate basis we have all used. Okay. In let's say Peskin. Okay. And if you write the Fear's identity in this alternate basis, then you will get this. So this aspect I'm not actually going to derive because it will take some time and it will use this property, okay, that I mentioned. Bar gamma 5 plus 1/4 psi bar gamma 5 gamma mu gamma 5 mu plus 1/8 psi bar. Okay. So in all of this, we have used the property that gamma mu nu rho is equal to epsilon mu nu rho sigma gamma 5. Okay, this is one property we have used in deriving this Fear's identity from this Fear's identity. Okay, is that clear? So now we will just do it for like chiral spinners. Okay, so suppose we have chiral projections of spins. Okay, yeah, and similarly for chi L and chi R. Okay, then you can show that chi L psi bar L is only psi bar L chi L PL plus 1/8 psi bar L gamma mu nu chi L mu nu, and chi L psi bar R is minus 1/2 psi bar chi L PR comma, where we have used PL PR is equal to 0. Okay, because when you have only left chiral ones, right, and you know the fact that PL gamma mu is gamma mu PR. Okay, so suppose you have chi bar L gamma mu psi L. What happens is that this is chi bar PL gamma mu psi L. This you can show that chi bar L is chi bar times PL, and this will become chi bar gamma mu PR psi L, and PR psi L is 0. So that does not show up in this relation. Okay. Similarly, the opposite is true here in the sense that if you only have psi bar r chi L, that is 0. Okay. Oh, somehow my screen is frozen. Can you guys hear me?
Yeah, we can hear you.
Yeah.
But my screen, it's not showing anymore. 1 second. Okay. Yeah. I don't know what to do. Yeah. So basically, this is the Fear's identity for chiral spinners, and we will mostly be using this when we go to supergravity, because we will work with chiral projections of spinners, and this is the Fear's identity. So, do people have questions?
Yeah, I think I should also point out that there are only 3 minutes left for Subbu's extended 15 minutes time.
Yeah. If there is some question, I can take it. Otherwise, I just have one point to say as an advertisement for the next lecture, and then I will stop. Just one equation to write, but somehow it is not showing the equations.
I have a question. It's probably very stupid confusion, but let me.
It doesn't matter. Yeah, tell me.
So when we started with this small gamma matrices, right?
Okay.
And then we took these antisymmetric combinations, and we defined this capital gamma matrices.
Yeah.
Right. So those capital gammas also are closed under multiplication and satisfy the Clifford's algebra. That is correct, right?
No, they satisfy this trace relation. Okay. Basically, they're constructed out of the Clifford algebra matrices. Okay.
Mm-hmm.
But they don't satisfy this algebra. I mean, this algebra is only defined for rank 1 gamma matrices. Okay.
Mm-hmm.
But you ask, given gamma matrices which satisfy this relation, what is the space of independent products of these matrices? Okay.
Yeah.
Those are these matrices, and they satisfy this relation.
Yeah. So now, there's this counting argument, which is this 4CR and then some more R.
Yeah.
Then when you change the basis, and before you and Subramanya had a discussion, it seemed to me that the new basis, it doesn't have the same number of indices. So if you do a counting there,
sorry, which basis? Oh, I see. You mean this gamma phi basis?
Yeah.
Oh, okay. This is just the fact that 4CR is equal to 4C 4 minus R. So the result will be the same. Okay, where is that?
I see. Oh, I see. Okay.
Yeah.
Okay.
Yeah, maybe I should have mentioned that, right? So this is, for example, this is 1 plus 4, right? And this is 4C2, so that is 6, right? And this is again 4, and this is 1, right? So in the end, you have 10 plus 6, so 16.
Okay, got it. Yeah, that's it. Thanks.
So I just have one equation to write, which will justify the point of this lecture. So we will just define Majorana spinors, okay? And we will discuss this in great detail in the next lecture. Majorana spinor is psi bar is equal to psi transpose C, which we knew, that is equal to the Dirac conjugate, I psi bar. Okay, and they both transform the same way under Lorentz transformations. Okay, so which tells us that this is a consistent condition in a relativistic theory. And since these are, because of these conditions, we will go from 4 complex component to 2 complex components, or 4 real components. Okay. I'll write real in quotation mark and we'll explain it later. Okay, in the next lecture, we will just use some properties of Majorana spinor and see its relation to the bispinor notation and go over to supersymmetry. Yeah, I'm done.
Okay, let us all thank Subbu by either unmuting yourself and clap or pressing the clap icon. So we will keep this Zoom room open during the break. If someone has any pressing question, they can ask now. Otherwise, I will stop the recording and people can have more informal discussions during the lunch break if they want.
Just a comment. So, so you can stop recording, Subramanya. I already started. So my point is that I have to cook and everything. So probably during the lunch break, just don't discuss any deferred discussions or anything, because probably at least I cannot be here for all the talk in the lunch break. Can we just do any physics discussion in Slack or some other time? Is it possible?
Yeah, sure. I mean, the point is that this is nothing hard and fast. I mean, people may want to discuss something independent of supergravity lectures or anything.
Sure.
So the Zoom room is open. People can make academic use of it as they see fit.
I'll be here for 15 more minutes. So if people want to ask informal questions, they can ask. But I won't say anything new.
So if there are no pressing questions right now, maybe I can pause the recording, and then people can ask more freely and more informal questions. Is that okay?
Yeah, I think so.
Okay. Okay, so welcome to our post-lunch session for the first day of ST4. We have a new lecture topic that is going to begin now. Biswajit Sahoo is a PhD student at HRI Allahabad, and he's going to teach us about soft theorems. So Biswajit, over to you.
Hello everyone. So thanks to the organizers for organizing this school. It's really hard time for everyone, but I think it's a good thing that we are really talking among ourselves. So let me begin by giving a little history of the subject which I am going to talk today, which is basically the soft theorem. So I will mainly focus on soft photon, and I will make two kind of soft theorem. One is the soft theorem for the photon, and the other one is for graviton. Okay. So the history begins by a work by Steven Weinberg. So you can see, I cannot see. So in 1965, he wrote a paper called Infrared Photon and Gravitons. So what he was doing, he was trying to study some infrared properties of the scattering amplitude in a scalar coupled to gravity theory or quantum electrodynamics. And what he was doing is that for an amplitude, if there are some external particles are photons or gravitons, and if this energy of the photons and gravitons are small, how these amplitudes behave. So this was what he was trying to study. And obviously you can see it is 1965, that time only quantum field theory was developing. There was there was nothing related to quantum gravity. People even don't think about these things. So what is the motivation of studying some properties of quantum gravity? So here is the motivation. So his first motivation is that because he can, so he will do. So only Weinberg can tell this thing, because he can, so he can do. The other thing is that he was thinking that, okay, probably studying some infrared properties, if something goes wrong, if he finds, then that could give some insight that what should be the quantum, that constrain the quantum theory of gravity, or how to study the quantum theory of gravity would be. But somehow he realized that nothing goes wrong. The other thing, I think, which is more promising, what he found is that suppose studying some kind of scattering amplitude with external photons or gravitons, now where I can apply this thing. So he was telling that even in his time, he studied suppose the soft photon theorem, and using this he tried to compute that what will be the thermal radiation from a sun. Even for the for the soft graviton theorem, what he was trying to study that, okay, what will be the gravitational radiation due to the sun, or like for the solar system when the planets are moving, and in such kind of cases. So he was studying this kind of process. So at least, like, though he has gotten a very little amount of gravitational radiation for such kind of processes, but at least it gives a hint that probably the scattering properties of the scattering amplitude can be used to study some classical processes. But this is long time, and I have given a figure where the citations of this paper is shown. You can see, like, up to around 2011 or 12, up to that time, not much work has been done in each year, which was based on this work. But suddenly what happens is that around like 2012 or like after that, there is a little bump in, and many people started working on this subject. Obviously, I'm not telling that this is not a motivation, like why you want to study this thing. But what I can tell is that what happens suddenly that so many people started working on this subject. So for that, I have to go to the next thing. So this actually started by the work of Strominger and his company. So what they tried to show is that 3 different areas of physics, which started long back and people were studying from long time. But what he has shown that actually these 3 subjects are not quite different, but these 3 subjects are related to one another. And this gives a real boost to this subject, and many people started working on. So let me briefly tell what these 3 different subjects are. So as I will go along, I will probably describe more. But so one corner of this triangle, you can see this is called Strominger's infrared triangle, where one of the corner you can see is basically a soft theorem, which is some property of the scattering amplitude. That's why I've drawn some Feynman diagrams. On the other corner, you can see asymptotic symmetries, where people are studying that what will be the asymptotic symmetry group of asymptotically flat space-time. Suppose you have a gravitational theory and you go to a large distance. So what you will expect the symmetry of the theory would be. And the other corner is called the memory effect, which is basically, you can think of like if there is some black hole merger problem or some astrophysical gravitational scattering. So for that process, so you put a gravitational wave detector and you see that when the gravitational wave passes through, the full scattering happens. What people can observe is a prediction that there will be a permanent shift between the 2 mirrors of the gravitational wave detector, even when the gravitational wave passes through. So before the scattering and after the scattering, there will be a difference between the distance of the 2 mirrors. So this is obviously a classical gravitational, like effect of the classical gravity. And these 3 subjects, like you can see that the time when this subject started, like the Soft theorem by Weinberg started around 1965, asymptotic symmetries, Bondi, Meissner, Jacques, they started around 1962, gravitational memory started by Christodoulou and many other people around 1987. And these 3 subjects are related to each other. That is what Strominger has shown us. And I will explain that if you start from the Soft theorem and do a Fourier transform in the energy of these soft particles, which is soft photon or graviton, you can go to the memory effect. And if you study the asymptotic symmetry and try to understand that, okay, corresponding to what this symmetry, what will be the OR identity, it translates to the Soft theorem. And you can relate also this memory effect and the asymptotic symmetry by some vacuum transition, like you have a degenerate set of vacuum in gravitational theory, and those are basically related by like vacuum transition. So these 3 subjects basically unifies in a sense. Oh, my iPad sharing.
Biswajit, maybe it's a good idea in the background to try to install the Zoom.
Okay. Just trying to connect it. So this relation between these 3 subjects basically really boosted this subject, and many people started working on this subject. But my motivation will be like, I will only, in this set of lectures, I will only like describe only 2 of the corners and their interrelations, not the other corner. Okay. So I'll only talk about the Soft theorem and the gravitational memory effect, or the maybe the electromagnetic memory effect corresponding to soft photon theorem and their interrelation. Oh.
Try stop sharing and try it again.
Okay.
I think this happens because like in HRI, all these devices will disconnect from the Wi-Fi regularly, or the Wi-Fi will disconnect from the devices regularly. So I think the iPad gets disconnected from the Wi-Fi.
Yeah, for HRI speakers, I think it's best if you log in from your iPad as well as Mac.
Okay, now probably it is
yeah,
visible.
It's good.
Okay. So my plan would be basically try to understand the relation between soft theorem and the memory effect, and obviously each of the corners in detail, like how the soft theorem is derived from scattering amplitude, or how independently the gravitational memory can be studied in classical general relativity, and then what could be the interrelations between them. But I will not talk about this asymptotic symmetry part, but I am happy to discuss in Slack on this subject as well. So then let me start by stating what is soft theorem. So the question we want to ask is that what is soft theorem? Okay. So consider a scattering amplitude in a generic theory of quantum, in a generic theory. And this scattering amplitude involves n number of finite energy particles which have the momenta, say P1 to Pn, and also have m number of small energy photons or gravitons. Photons and or gravitons. And those have momenta, say K1 to Km. Now what you do is basically you expand this. So let me call this scattering amplitude to be gamma Nm. Now what you do is basically expand in power series of the soft. So what I will, these finite energy particles I will call to be hard particles, and this small energy photons or gravitons, those I will call to be soft photons and soft gravitons, and this K1, K2 to Km, those will be the soft photons or soft gravitons momenta, so I will call them to be soft momenta. So then what you do, start with this amplitude and expand it in power of soft momenta. Then obviously this expansion you always can do, and you can find out what will be the coefficient of this expansion. So get the coefficients of this expansion. Of this power series expansion.
Biswajit?
Yes.
What do you mean by finite energy and small energy? Because these are like This is not a Lorentz invariant statement, no?
Okay, like yeah, so you can think of like each of these you can think of like k mu, each of the component. So you define this each of the component of the k mu to be smaller than each components of the momenta.
Okay.
So in that sense, each of the components, like you can think of like if this k mu you define to be say omega times some null unit vector, then you can think that this omega is much small than like the energy of the say particles.
Okay. 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 Thanks.
So this is in any reference frame?
Yeah, I think this could be yeah in any reference. At least energy you can think in terms of energy in any reference frame. This will work. I hope. Yeah.
Just a small comment. Hello.
Yes.
I think one can define this low energy by going in a rest frame and defining the component there.
Means in the center of momentum frame, if you go and define.
Yeah.
Yeah, then there you can define in terms of energy also. Yeah, I think so. But I think this is okay.
Sorry, which one is it? Center of momentum frame or rest frame? The two are different.
I think it will be center of momentum frame.
Rest frame for what? These are null particles.
Yeah, these are null.
Yeah.
These are null particles. So then what Soft theorem predicts is basically this coefficients of this power series expansion up to some order. So what Soft theorem gives you?
We have a question in the comment from Anirban. He's asking, is M a finite number?
Yeah, we are considering M to be a finite number, but we can take M to be large also.
But large but finite or infinite?
Yes, large but finite. In a sense, we can think of this M into omega, like we can take M to be large, but M times omega, which is the total number of gravitons and its energy, say each of them are order omega. So M and omega, we can always try to think is smaller than the each of the particles, each of the finite particles energy.
Okay, does that answer your question, anyone? Okay, go ahead.
Okay, so what Soft theorem gives is basically Soft theorem gives this coefficients of this soft momenta expansion. Momenta expansion. But this like you can see that always you can expand this thing. But the interesting thing is that what Soft theorem will tell us is that in this expansion, up to some order, if you start with this gamma nm and try to expand in power of soft momenta, up to some order you can show is that this amplitude mn plus m point amplitude can be written in terms of an amplitude which does not have any number of soft particles, which is gamma n, or you can call it, I think, gamma n0 in the same notation. Sorry. And what will be this S? So this S could be function of the polarization of the soft particle, the momentum of the soft particle. So let me put all m number of particles, and also can depend on the polarization of the finite energy particles, which I will denote I runs from 1 to n, and their momentum pi, and also possibly their spin, which I will denote by sigma s. So S would be function of these variables. And we want to see that without really specifying what theory we are studying, how much we can get in the soft factor S, which is universal, in a sense theory independent. That means it depends on only the scattering data, which are you can see the asymptotic particles momentum, polarizations, and their spins. So this is the goal. And let me before going, let me give the result that how much order expansion we can predict. It turns out that in the soft momentum expansion, soft photon theorem is universal. So universal means it only depends on the scattering data, not on the theory. Up to only leading order.
Biswajit,
yes.
There is a question. He's asking, can we do similar expansion in m number of ultra relativistic particles and other finite energy particles also?
In n number of or m number of?
M number of ultra relativistic particles.
Yes, I think you can do like even these n particles means ultra relativistic means you are considering these are to be massless particles.
Arkajyoti, maybe you can unmute yourself and ask the question yourself.
Hello.
Yes.
So I was wondering whether in spite of having m number of low energy particles, suppose I have a setup where we have very high energy particles and some other finite energy particles, and in that setup can we expand the scattering amplitude in terms of this high energy modes?
I think like if you try to expand in terms of high, like if you consider m number of massless particles to be high energetic, you may not get like you may not able to write this gamma n plus m in terms of gamma n. So it may not factorize in that way.
Okay.
I have a question.
Yes.
Since we are talking about a reference frame, so suppose that I have a detector at some reference frame, right? I mean, I'm at the detector's reference frame.
Okay.
And this detector can measure up to some maximum wavelength.
Right.
Right. So I'll call all the particles that have wavelength more than that soft particles, right?
Okay, like here, the definition of the soft particle is not like that, not like detector dependent. Here, what I am calling is the soft particle is basically the massless particles, which has energy is less than the finite energy particles. Like the kind of soft particles, what you are telling, those are detector dependent, and these are not even like one cannot observe this kind of particles, because like you can think from the scattering center, if you are putting your detector at distance r, then obviously the wavelength which is greater than r you cannot observe by this detector. Right. So those are obviously soft, I agree, but we are not talking about this kind of soft particles. In a sense, like first of all, we are not like here we are thinking of like we are putting all the detectors at infinity. But in the classic, like in the actual process, actually there is no infinity, so I have to put in a finite distance, then there will be such kind of a cutoff. But here I am telling soft means basically like the massless particles which has energy less compared to the finite energy particles energy.
Biswajit, I think there is a clarification that so Mrityunjay is making. He says that a more Lorentz invariant notion of what we mean by the low energy can be given by saying that the quantity pi dot k by pj dot pl, where I, j, k are the indices corresponding to the finite hard energy particles.
Right.
So it's the ratio in which you do the expansion. So that is a Lorentz invariant.
Yes. So sorry. Yeah. So probably I should mention. So basically, let me write it down. So like pi dot k upon pi dot pj. So that will be much less than 1 for any ij, for all ij. Okay. So this you can define in a more Lorentz invariant way, the softness. Thank you. Okay.
But does this this definition automatically imply that if I have, say, a large number of soft gravitons, that the total energy will be less than the individual energy of all the finite energy particles?
Okay, actually in the scattering amplitude sense, this thing is not needed, even like the large total energy of the gravitons. But when you take a classical limit and try to understand this large number of coherent set of graviton as a gravity wave, then there one needs this assumption. But in the scattering amplitude level, you are thinking each of the gravitons to be a different particles. So here this constant, like which I explained earlier, that total number of energy have to be large, that constant would not be needed.
Okay, thank you.
Biswajit, Anirban has a question. He's asking why masslessness is needed why masslessness needed maybe just much less momentum can't be sufficient?
Okay, actually masslessness is needed because you can see that if the particles are massive, then this factorization will not hold. And the other thing is that like we have like here, at least for the case what we are studying here, also like for the photon or the graviton case, the way we will derive gauge invariance is also we need to impose. So I think masslessness is immediate, like this is needed even for if you study like scalar soft theorems, there also one needs this masslessness. But also with this we need here the like gauge invariance also, which I will describe.
Yeah, maybe I can add a comment that the
Yes.
soft theorems are a consequence of the infrared properties of the theory, and the theory where there are massless particles and the theory where there are massive particles but the mass may be very small have very different infrared behavior.
Yes. So I am disconnecting. So let me state the statement without writing. So for the soft photon theorem case, what one can see is that only at leading order it is universal. From the subleading order, one can see that the theory dependence will appear. And if you try to study soft graviton theorem, there what you will see is basically up to subleading order in the soft momentum expansion, the soft theorem turns out to be theory independent, that is universal. But if you go to the next order, which is a sub-subleading order in the soft momentum expansion, it turns out to be dependent on the theory. Okay, don't know how it is working.
Biswajit, just check if your iPad is connected to the Wi-Fi.
Yeah, it's connected. I think it's now.
Yeah, it's okay.
Okay. So what happens is that like if you have
one question, you are going to show the factorization, right?
Yes, I'll give the factorization process, like how one derives even without having much information of the theory. So for the soft graviton case, it turns out to be universal up to subleading order. Okay. Okay.
Biswajit.
Yes.
Probably very dumb question. Let's go back to the last slide. So the thing that you wrote in the beginning. So gamma nm equal to S gamma n0. So this is an all order statement, right?
Okay, so this is the disclaimer I have written in the next 2 points. So this is not actually in all order. Like it turns out that so only up to the, like if you try to expand in soft power, so I think maybe I should put ... So what happens is that up to like one can show that up to, in a sense, sub-subleading order for the soft graviton theorem and up to subleading order of the soft photon theorem, one can show these factorizations. But in that case, in the subleading order of the soft photon and the sub-subleading order of the soft graviton, there will be some theory dependent part, but still one can write in a factored form. But after that order, there one can show that some part will factored out, but there will be some part which one cannot write in terms of gamma n0. So it's not all order expression.
Okay. I was confused with this universal part of it. Fine, now it's good.
Hi, Biswajit.
Yes.
Can some of the finite energy particle in the scattering process be massive in this case?
Can some of the finite energy particles? Yeah, finite energy particles can be massive, massless, anything.
Okay.
So we don't have any constraint on the finite energy particles. They can have that. They can be high spin particles, anything.
Okay. Thank you.
Okay.
So let me one last question. Is this factorization dimension independent, like space-time dimension?
Okay, so I'll try to derive how much dimension independent way one can do, and then I will show that actually in four space-time dimension and some of the, like I will try to derive using some assumptions, and then I will show that in four space-time dimension some of the assumptions breaks down and one have to treat four dimension spatially. But with some assumptions which I will now just describe, one can show that this will be dimension independent statement.
Okay.
If these assumptions are valid.
Yeah.
We have a question in the comment, Biswajit.
Yes.
Devorshi is asking, is there a similar collinear theorem maybe related to collinear IR divergences, or maybe the collinear divergent amplitudes factorize in the same way?
Okay, it's obviously for gravity theory, even the external particles are massless, there is no collinear divergence. So Starman and Akori, they have the paper. But for the QED theory, if the external particles are massless, then there will be collinear divergences, and for QCD obviously. And for that, I'm not aware about whether one can write in terms of this factorized process. But yeah, I'm not sure that one can write n plus m point amplitude to be in terms of n point amplitude if one take collinear limit, but there may exist. I'm not aware of.
Biswajit, why are the external particles massless in gravity in soft graviton theory?
Oh, it means the external particles can be massless also, right? Like if you study say 5 graviton or 6 graviton amplitude,
they can be massless, but are you saying they have to be massless?
No. Like for collinear divergence, what happens is that if you are studying say single soft graviton theorem where only one number of graviton is external, so in that case, if you try to study what will be the collinear limit, for that you need some other external particles also massless.
I see. Okay.
So in that sense, I told that like to get a collinear divergence, the external particles have to be massless.
Okay. Yeah. Thanks.
I have a question.
Yes.
So when you expand it in terms of the powers of the soft momenta,
right?
What type of an expansion is it? I mean, is it a convergent? I mean, what in what sense is it an expansion?
Okay, first of all, I will use like in a sense, you see that the thing what is written like pi dot pj over pi dot k. This is so maybe the reverse way. So this is much greater than 1.
Mm-hmm.
So in a sense, like, or if you take the reverse, then it is less than 1. So I can always expand in power of k. But obviously, since I don't have the information about the all power of k, so I cannot obviously study that whether this series converges or diverges. So the convergence, the radius of convergence is not known. But from here, since I have a parameter which is small to compare to, I have some other parameter with the finite energy particles. So I will expand and try to see that how much information I can recover.
Okay. Is there a sense in which there is a factorization? I mean, like up to all orders? Is it at all possible? Like,
okay, like what happens is that people have tried that to give infinite order soft theorem, but it turns out that like say let's say soft photon theorem case, after subleading order, if you try to study say subleading order soft photon theorem, it turns out that some part can be written in terms of some operator operating on the endpoint amplitude, but there is some other part which cannot be written as a factorized part in terms of endpoint amplitude. In that sense, this full thing that gamma n plus m can be written in terms of some operator operating on gamma n, it's after subleading order, it breaks down for soft photon theorems.
I see. Okay.
So, but I hope that maybe for the classical soft theorem, which I will describe later, there maybe one can, by brute force, one can try to get all order result.
I see. Okay.
But that will be obviously theory dependent. Okay. So what I will do is I will try to derive the soft photon and soft graviton theorem at one go. So for that, let me I will now state the assumptions based on which I will try to derive. And if these assumptions becomes there is some problem with the assumptions, then we have to treat this like some space-time dimension. Suppose this assumptions breaks down, then we have to treat this separately. So I'll assume only two things. So this is basically what I am doing is developed by Ashok Sen. So I'm calling it as Sen's covariantization prescription. So first assumption is that the theory will be described by a one particle irreducible effective action in D non-compact space-time dimension So what that means is that suppose you have a UV complete quantum theory of gravity, and suppose you just try to derive what will be the 1π effective action by integrating out all the quantum fluctuation, and what you get is basically 1π effective action. But since you started with a general covariant coordinate invariant theory, and suppose it has a U1 gauge invariance also, then this effective action whatever you have, that will also be general coordinate invariant if the theory don't have anomaly. This has a general coordinate invariance, and also if you have some global UL transformation and some U1 gauge invariance also, then it will be also say U1 gauge invariant. So I am considering both of these two because I will study soft photon and soft graviton theorem simultaneously. So it has a U1 gauge invariance also. Okay. So this is one of the assumptions. Now, if you see, like if you have a 1π effective action, then you have a action for the full quantum theory. And now if you just draw like the tree level Feynman diagrams, that will compute your full loop amplitudes. So with this 1π effective action, only tree level, this is the property of 1π effective action, gives the full or loop corrected S matrix. The next assumption. So is there any question with this assumption?
Yeah, Biswajit, one question.
Yes.
So about this non-compact space-time dimensions, for example, if you have some like complicated manifolds with some compact dimensions also,
right?
Like, so these factorization theorems, do they depend on the compact dimensions, or
So
some
that,
assumptions from the compact dimensions?
Okay, actually those already goes in the derivation of the 1π effective action, and since like we are studying the S matrix, and the S matrix is defined only in asymptotically flat space-time. So and these are the D number of non-compact space-time dimensions where we will define, and the compact dimensions, like those are already gone through in the definition of 1π to derive the 1π effective action. Like you are basically all the other modes basically already you integrated out, and you got a 1π effective action. And if there is some non-compact space, like either some compact space-time dimension, then obviously there will be some infinite number of towers of particles. So that will already appears in your 1π effective action.
Okay.
So those could be external particles as well. Okay, I don't know. I don't think external
particles. If I'm not wrong, like Mrityunjay has worked on this Kaluza-Klein reductions and soft theorems, right?
Right.
Yes. So what was the question? Can you repeat again?
So I was asking about the assumption regarding these non-compact dimensions. If there are some compact dimensions present, so how much of these factorizations depend on those compact dimensions?
So not much actually. So factorization still goes through. I mean, only thing you demand from this compactification is that you don't produce any IR divergent terms. And that is guaranteed if you are above 4 dimension.
Yeah, I think like if you do a different, like if you have different two compact space-time, then you will have two different 1π effective action, and that can affect your non-universal piece, which is the not theory dependent piece differently. Like it will affect to the subleading order soft photon theorem or the sub-subleading soft graviton theorem and onwards.
Okay.
So I'm correct, right, Mrityunjay, because you have some non-universal piece depending on the.
Yes, but yeah, that happens because usually universality is there only up to subleading term in the soft graviton case, and up to leading term in the soft photon case. But that happens, I mean, that follows because those leading case of soft photon can be just derived using the U1 invariance of the theory. And the subleading of the graviton, up to subleading of the graviton, can be derived using the diffeomorphism invariance. So beyond that, I mean, these symmetries, I mean, you cannot use these symmetries to derive the form of those operators. And so when you derive this soft theorems from compactification, then essentially the universality term follows up to subleading for the graviton case and leading for the soft photon case. But beyond that, because there is no symmetry to dictate the form of this thing, I mean, symmetry doesn't fix the form beyond the subleading case. So that is why this form, you get this non-universal pieces.
Okay, thank you. So let me give the second assumptions. The second assumption is that, like, now if you start with this 1-pay effective action, then I told that, like, we will derive using sense covariantization prescription. So obviously I will later explain what is this covariantization, but let me give the assumptions is that after covariantizing the action, so from the covariantized action, one particle irreducible effective action, if you try to derive any vertex, so in vertex, which involves some soft particles, so it can be soft photon or soft graviton, involves, okay, maybe I'm writing, okay, I don't know. So the assumption is that this vertex should not contain one over soft momenta, that is soft momenta in the denominator. Soft momenta in the denominator. Say for example, you are considering two finite energy particles and one soft particle. This is soft particle with momentum k, and this is some finite energy particle. This is some 1pi vertex. So that should not contain any 1 over soft momenta. So this is not allowed. Okay. And what we will see is that this is the assumption which breaks down. I will explain later. In d equal to 4. So we cannot apply this covariantization prescription to derive soft theorem for in space-time dimension 4 for loop amplitudes. But we are working in a general D, and let's see in general D how much we can proceed with these two assumptions. Okay. So now I will explain the strategy of this covariantization procedure. The strategy. Okay. The first, already you have corresponding to the theory some general coordinate invariant and gauge invariant 1-pay effective action. Then you start expanding this effective action about all of its fields about their vacuum expectation value. So expand. Okay, maybe I should tell before even. Okay, I think it's fine. Okay. So expand this 1-pi effective action about all of its field vacuum expression value. What will do that thing? So if you do this thing, then that means basically in the 1-pay effective action, after expanding, you won't have any term which is like only linear in one of the finite energy fields. So it will break up that all one point vertex or all, or maybe I should mathematically write that what that will do is that any of the field in this 1P effective action, its Beckman expression value, you put to be phi 0, and you call that the fluctuation phi 0 plus say pi, and then yes.
I think the screen is frozen or something.
Oh, sorry, yes.
No, it's coming with a lot of delay.
Yeah, it's a huge delay.
Okay, yeah. So should I stop sharing?
No, Biswajit, you continue. I don't think by stopping this will be remedy.
Okay, sorry. Okay, so that is what I have written earlier, that basically you expand all the fields about their vacuum expectation value, so that now in your 1P effective action you don't have any term which is only linear in one of the field. It will always start from the quadratic part. Okay, and then what you do is basically you have the general coordinate invariance and also the gauge invariant. So obviously you have to gauge fix, otherwise you cannot determine the propagator corresponding to the fields. So you gauge fix the action using some low range covariant gauge fixing condition. Okay, but you see that this 1P effective action can have fields which are photons and gravitons also. So you already gauge fixed it. Now,
Biswajit?
Yes.
Can you clarify, like, what did you mean when you said that that there won't be any term that is linear in that field due to this condition? Because linear in field, unless it's an auxiliary field, anyhow there won't be any term, right?
Okay, like what you do is that, like, to start with, since you have a 1P effective action, it can start from linear in field. Now what you do is that you just have, like, you now you have a effective potential, and basically what you do is that you use the minimization or like extremization condition, and you find some classical value of the field.
Oh,
right?
I see.
And
right.
then you expand about this thing, then the linear term will be always proportional to the equation of motion in that sense, and that will vanish.
Okay.
Because always del v del phi is 0 you are putting.
Right. Okay.
Right?
Yeah.
Okay. Now after this, now you have a gauge fixed action. So let me write that what would be the more general form of this gauge fixed action could be. So I will explain all these terms in a minute, but let me write down how it can look like. So this will be the general form of a action. So let me tell, like, see, you can see that I have written that n always greater or equal to 2. So for n equal to 2, that will be the basically the kinetic term. And for 3, starting from the 3, it will be the interaction vertex. And I don't have like much of the information. And Vn is basically the vertex factor or the kinetic term. And this could be more general, as much general as you can think. And I will not give any information about what these Vns are, except from that this action have to be invariance under, like I will explain later. So some global invariance and other things. And then what will be the phi alpha? So what I am denoting by this phi alpha is basically all sets of field, set of all the fields present in your theory. Okay, so what you have, suppose your theory have 3 kind of fields. Say for example, your theory have 3 kind of fields, say a scalar field, say a complex scalar field, a gauge field, say a graviton field. These are the fields of your theory. So what you do is basically, so this phi, suppose this phi and phi star are the fields. So what you do is that you write all this thing in real components. So I will use always a real component field. So you just write this to in terms of 2 real component scalar, phi 1 and phi 2. And you define your phi alpha, that notation which I denoted is basically starting from like phi 1, phi 2, 4 gauge field, and 10, like, sorry, in d dimension d number of gauge fields, and d into d plus 1 number of, d into d plus 1 by 2 number of metric field. So you organize all of them in a column, and this is the more general form of this phi alpha. So you can see what is this phi alpha is basically, this is a field in a reducible representation of the Lorentz group. Okay, so this is the more general form of the phi which I am using, which contains all the field content of the theory. Now if I go back, so see, I have written this action in a momentum space. So first of all, these phi's are basically the Fourier transform of these fields. D is basically the vertex factor, also contains the kinetic term for n equal to 2, and there is a momentum conserving delta function. So the goal will be that without much information of the theory, which is basically the content of the theory is this V, how far we can determine the soft factor or study the amplitude and try to extract the soft factor. This will be the goal of this lecture.
Hi, Biswajit.
Yes.
So is this S effective is gauge fixed already, right?
Yes, yes, we already have gauge fixed it.
So I had another question. So instead of taking the Lorentz covariant gauge fixing condition,
right,
suppose you have taken the gauge covariant.
Okay, so I am not doing this because you see I have expanded all the fields. Like if you have a matrix, say, so I have expanded the action also in terms of the field of the metric and all these things. That is why I am adding a Lorentz fixed gauge, Lorentz invariant gauge fixing condition.
Okay.
Otherwise, like the Lorentz covariant will have infinite number of terms.
Okay, thank you.
Okay.
Biswajit.
Yes.
Abhishek has a request. He says that it will be helpful if you don't change the slides quickly.
If I, okay. So I'll stay on the slide for some time.
Yeah.
Okay. Thanks.
Subbu also says the same thing, especially the last line of the slide.
Okay. I was thinking maybe I'm going a little slow, so fine. Okay.
I missed the argument about using other sort of gauge fixing condition. Can you repeat?
Okay, so basically I am, first of all, I want this action to be Lorentz invariant. So I want to add some Lorentz covariant gauge fixing conditions only. Means in a sense, if you think like for gauge theory, I will use like Lorentz gauge condition, del mu mu whole square. Basically I will term 1 by 2 xi times and del mu whole square kind of term I will add. If I study, say, if I have some gravitational field, so what I will use is basically the de Rondar gauge fixing term I will add. This kind of things I'll do. So what Orkut was asking is that can one use low-range covariant gauge fixing condition, that in place of like these things, can I use like say d mu h mu nu times basically d mu h mu nu square. Can I add say d mu h mu nu times d rho h rho nu kind of terms, which are more which are basically you can think of more covariant way of doing this thing. But what I am explaining is, since I expanded all the metric components and all the other fields in terms of their components about their vacuum excitation value, so already this d mu contains say gamma, that also I have expanded in a sense in terms of h. So I have the action now which is basically expanded in terms of all the fields, the metric fluctuation and all these things. So that is why I am adding a low range, only the low range covariant gauge fixing conditions. Is it fine?
Biswajit, I think your screen is stuck.
Yes, I couldn't see the writing.
Yeah, your screen is frozen.
Okay, but I think this is just the statement which I told. So, okay, but the next slide is also not working.
Can one of the other contributors of the keynote share the screen? Maybe that will make it easier.
I'm just trying to do once again.
So presumably, like say choose for gauge fields, choosing some axial gauge or something like that, that would be precisely.
Yeah, since that will since that will break the Lorentz invariance, so I will not use this thing. I want to keep the Lorentz invariance of the accent to be whatever it is, like it is Lorentz invariant.
I mean, it would become very difficult, I suppose. Right?
Okay, I'm not sure about how much difficult it would be.
Yeah, I think it will be horrible.
Okay.
Okay. So how far we go is basically we have explained only two of the point of the strategy, that we gauge fixed action, and we have written down the general form of this gauge fixed action. Now, see, from this action we also could derive, since this action also contains the fields which are like gravitons and the photons, and we can also try to derive what would be the vertex for the gravitons and photons, and we could take the soft limit as well. But since we know that these gravitons and photons, they couple to a theory using the gauge invariance, so it's better that since we are trying to understand that if there is some external photons or gravitons, we want to get the vertex. So it's better that we covariantize the action with respect to those kind of fields. In that way, like since up to some order, like the coupling of this gauge field or the gravitons, those are universal in a sense, fixed by the gauge invariance or general coordinate invariance. So it's better to it's better to use this information once again. So for that reason, what we will do is basically we will covariantize this action with respect to these soft fields, the soft particles fields, which are the soft photons or the soft gravitons. So the next thing which I want to do is basically covariantize this effective action, whatever we have, with respect to soft photon. So I'll do both photon and graviton background simultaneously, and graviton field. So what this covariantization means is basically, see, you have now all the gauge invariance goes and you have expanded all the fields. Now you're now what happens is that asymptotically, like now you are considering a theory which is in the background of Minkowski metric. So now what you do is that basically you replace eta mu nu by eta mu nu plus 2s mu nu. This s mu nu will call to be the soft graviton field. So 2 is just a normal like convention. usually one use 2 kappa, where kappa is square root 8 pi g, and we are setting the convention that 8 pi g equal to 1. This is the soft graviton field, and all the covariant derivative whatever we have to use, like, sorry, all the ordinary derivative whatever we have to use the covariant derivative for them. And since we want to work in like external particles, phi can be boson, fermion, anything. So it's better to work in tangent space index, not in Card space index. So we will, since the fermions are there, so we will use the tangent space notation always. So this alpha you can think of is basically the polarizations of the fields in the tangent space index. And then, and I'll use the notation that A1, A2, all these indices, those basically gives, the space-time index for the tangent space. This is the tangent space index. And as mu nu will be the Card space index. So basically, suppose you have a phi field with polarization alpha and some derivatives are operating on it. So in Vn, such kind of terms could be there in your action when you expand it. So then what we will do is basically, we will covariantize this part. Covariantize means first what we will do is that we will first, using inverse Vlbine, what we will do is that we will make this tangent space index to the Card space index, and then we will write down the ordinary derivatives by covariant derivative, and the covariant derivative with the metric, which is the metric with the soft graviton metric. In a sense, let me call this the soft graviton metric GS mu nu. So in this metric, you just write down the covariant derivative. So let me write down the expression. So this is the inverse Vlbine. Mu n, and then you have d mu1 dot 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 d mu n operating on this field phi alpha. So this is what the covariantation means. One is that, like, you replace your metric by the soft graviton background, which is eta mu nu plus 2s mu nu, and all the ordinary derivatives you make by covariant derivatives. So let me give the definition. Yes.
Biswajit, probably you have to symmetrize the indices in the covariant derivative.
Okay,
otherwise,
actually,
it is ambiguous. Right? Because
yeah, I think
covariant derivatives don't commute, right? Whereas partial derivatives commute.
Right. So what I can think, like, so I can write in this form, but also what you are telling that I can write in terms of covariant derivative, but in terms of symmetrized form. But you know that the difference between those will be Riemann tensor or the higher curvature terms.
Yeah.
Right. And since I will only look up to the subleading order, where basically only single moment, soft momentum in the vertex could be allowed, so that will not affect to me. So I can do both up to subleading order. So maybe I can use the symmetrized notation here.
Okay.
But it will not matter in my analysis.
I mean, I find that quite confusing, because the way I think about it is that, like partial derivatives go to like symmetrized derivatives, and the rest is the non-minimal coupling, which is the
Okay. Yeah. I think it's fine. Yeah, both it will work up to subleading order. It will not affect. But what you are telling, in subleading order, that will affect. And one should write symmetric form, and then the rest of the part Riemann tensor dependent one can add by hand as a non-minimal coupling.
Yeah, that's what I mean.
Thank you.
Thanks.
Okay.
These covariant derivatives are also gauge covariant derivatives.
Yes, it has both gauge and both. So I'm writing the expression. So if there is single covariant derivative, say on field phi alpha, so this definition is like del mu over phi alpha minus I will explain all the terms, q beta mu of phi beta. This is the term. Then there is the spin connection part, which is half of omega mu AB sigma AB alpha beta then phi beta. Right. So this is the, like, if there is a single covariant derivative operating on the phi alpha, this is the definition. This is how the covariant derivative is defined. So you can see here I have written a charge operator in place of a single charge, which is Q alpha beta, which is, you can think of a matrix. And so this Q alpha beta I have written in this way because I want to study the soft total and soft graviton theorem in one go. And there could be some scalar fields in phi which don't have a U1 gauge invariance. Or if there is some complex scalar, then I have broken to write it down in terms of two real scalars. So you can think of this is basically, in a sense, in SO2 representation instead of U1. So this Q alpha beta is basically the charge matrix, which basically, if it operates on the fields, it will give the corresponding charge of the particle. If it has don't charge, then it will vanish. If it has a charge, it will give some value. And we will always think of, in place of U1, this is a SO2 SO2 charge matrix. So let me write it down. So this is a SO2.
Biswajit?
Yes.
Could you say something about the background independence of the method?
Okay, so yeah, I wanted to avoid this thing, this background independence. So like you can think of like this covariantation prescriptions I am changing from Minkowski to some other background, some in terms of some eta mu to S mu nu. So that assumes that the theory should not change under this background. So what happens is that, first of all, I don't know too much about string field theory, but I can state the statement about the background independence is that, like, one can show is that if you change your, this is basically what you are doing is basically you have a target space and you are basically changing the metric of the target space. And that will give, like, if you are studying a super conformal field theory corresponding to the string theory, so that will change one super conformal field theory to the other super conformal field theory. And one can show in string field theory that by this S mu nu, by the metric change, this is a marginal deformation, and I am not quite aware about what marginal deformation means, but this effectively means is that using field redefinition technique, one can relate these two different theories. Probably Subramanya can tell much more about background independence, but I think for the working knowledge, this should be enough.
Yeah, I think we don't need to go to string field theory. I think it's enough to say that you're assuming that whatever 1PI action you wrote, you are assuming it to be background independent, and the statement of background independence is that if you change the background, like here you have taken eta mu nu to eta mu nu plus S mu nu, the S matrices are actually of the two different backgrounds. The S matrices are related by a field redefinition, and we know that a field redefinition doesn't really change the physical S matrix. So in that sense, the 1PI action is background independent. And the only known example of a physical theory where this happens is string field theory, but that need not be relevant for this discussion.
Okay, so this S mu nu can be any background metric? Or is it has to be specific to the...
It has to be a valid background of the theory. So it has to, it cannot be something which generates tadpoles and everything. So the 1PI action, Biswajit told that the 1PI action is being sort of expanded about a stable vacua. So when you change that vacua, change that background, that new background also has to be a stable vacua. So as long as it's a stable background, everything else is fine.
Does it have to be asymptotically flat, this new background?
Yes.
Yeah, obviously. Otherwise, the S matrix. So the new background should also admit a asymptotically spaced time, a flat space time.
Okay.
So here, so one of the things is that this Q, we are considering a charge matrix corresponding to this SO2.
Just a comment.
Yes.
So if your background is not asymptotically flat, then there will be corrections of the order of the 1 over R and something. Yeah, 1 over R. Suppose you are studying soft theorem in de-Sitter, then you will get the usual thing, and then there usual thing. I mean, in the flat space, and then there will be correction of the order of curvature of the space.
Okay, means I'm not also sure that whether there one can define a S matrix like
without asymptotic flat condition. How do you define S matrix?
Yeah, I mean you need the Lorentz. So I mean you can treat this as in a perturbative way. So up to lowest order, suppose your background is eta mu nu Minkowski, and then there is a correction. So.
But I don't think de-Sitter can be thought of as a perturbation to the Minkowski.
Yes, that is true.
As long as it's a perturbation to the Minkowski, I think it's fine. I mean, the perturbation, as long as it doesn't grow and it doesn't create an instability, I think it will still be an asymptotically flat space time.
I mean, one thing one can say is that if your energy of the soft particles are much less than 1 over the radius of curvature of your space. Then even in de Sitter, you can apply the Soft theorem, because for example, we use Soft theorem even in the de Sitter space. Like our space time is de Sitter, but we still use this thing. So the assumption which goes there is that your energy of your particle is much less than 1 over radius of curvature. I mean, this your scale of the de Sitter space.
Okay. Yeah. Means okay. Means just I had I have a confusion that whether one can define S matrix. But after getting the result, the statement what you are telling that one can use this result even in de Sitter if the wavelength is larger than the radius of the de Sitter.
Yeah.
But
I mean, we cannot define S matrix in de Sitter, but yeah.
Maybe the classical limit of the Soft theorem can be accommodated, but as far as the amplitudes are concerned, I think we don't know how to define it except for the asymptotically flat spacetime.
Maybe in de Sitter or ADS, there can be a constraint of like Soft theorem in correlation functions.
Actually
sorry.
Okay, let me make the statement. Actually, for the Soft theorem, one needs to use the on-cell condition, because I will show basically the external particles have to be on-cell to get the factorization property. So in terms of amplitude, it's in terms of correlation function, it's not clear that this factorization holds or not, even in flat spacetime.
I mean, there is a relation between the flat space S matrix and correlation functions in CFT.
Right.
Actually,
right.
so maybe what Arindam was suggesting, maybe something related to that. Maybe?
Yeah. Like what happens is that there one can study the property of this word identity in a word identity point of view. Currently, people are studying. So one can study the what will be the, if you start from the symmetry and try to study the word identity of the correlation function, and then take large radius limit and then use on-cell conditions to get that what will be the flat space limit the factorization property would be.
Precisely.
But in general, okay, without taking large radius limit, it's not quite clear that
you have to take that flat space limit. Otherwise, I don't think like that statement.
Okay. Okay. So here another one thing I have written, which is basically, let me maybe copy this expression in the next slide and explain the other things. Okay. So but you can see, like, first of all, this Q is basically some charge matrix for the SO2 transformation. And the other thing is that what is this omega mu AB? So this is, the spin connection. Which
Sorry,
have been, yes.
Why does this Q alpha beta representation of the SO2 group? I missed that one.
Okay. So this, first of all, this alpha beta contains both the polarization index of the particles and if there are multiple number of particles.
Okay.
Right. So now, like, suppose you consider like phi to be, suppose there is a complex scalar which is phi1 plus I phi2. Sorry. And then phi star to be phi1 minus I phi2. But we are calling this phi matrix, we are writing in terms of phi1 and phi2, not in terms of phi and phi star. So now this charge matrix will have off diagonal element, right? One of them probably will be some Q or half of Q, I forgot. Say Q charge, and the other one will some minus Q charge or such kind of thing. So that is why I have written this is a matrix form.
Okay, but this transformation, are you restricting only to U1 gauge transformations or in more general diffeomorphisms also?
No. So here, this corresponding to this mu gauge field, this is a just U1 or SO2 equivalently. And the general coordinate transformation, this information is incorporated in this term in the covariantation procedure, which I will explain now.
Okay. Thanks.
Okay. So this is, that the spin connection, which is defined as a covariant derivative over the VL by, which is, let me write down the expression, which is E nu A d mu of E to contract it. So there is this new index. B. So all the indices lower and up, lowered by just eta, like here in the E, actually E is defined nu to be below, so that's right, contracted by eta.
Biswajit, I think
sorry.
Frozen, I think.
Oh, okay.
Is your Wi-Fi really connected to HRI internet?
Yes. Okay. My Wi-Fi is connected to HRI.
So it would be good to figure out why this happens.
Okay, I'm sorry. Yeah, maybe I'll from next lecture I will connect to differently. That would be good. Okay. So what I have written here is the definition of the spin connection omega mu AB, which is E nu A, D mu is the covariant derivative, and this is now the covariant derivative. Obviously, since graviton has no charge, so this covariant derivative is only the covariant derivative containing the metric information, the connection information, and the BL by N. And so up to the order, like since first I want to look at only the single soft graviton and the single soft photon theorem. So for that I need a vertex which involves only one soft photon and the soft graviton. So it will be fine for me to keep only linear order terms in S. So up to that order, this is the exercise. If you calculate, it turns out that this can be written as del B of S mu A minus del A of S mu B plus some order S square term, which are not needed to study the single soft photon graviton theorem, but would be important for if we try to study multiple one, which I will describe at the maybe next in the next lecture. So okay. So up to this point, is there any question? Okay.
Can you repeat the last line, because the screen had frozen just before you wrote down the last line?
Okay. The last line, what I am telling is that since I want to study only the single soft graviton theorem, so I need a vertex which involves only one external soft graviton. For that, I need in the covariant transition procedure only the terms which are linear in S. So if you just now put all the expressions of the metric, like if you put that whatever I have written, that your soft graviton metric to be eta mu nu plus 2s mu nu, and with this you can write down what will be the VL by N, which will be delta mu A plus S mu A, the inverse VL by N, which will be A mu, which is delta A mu minus S A mu. And if you substitute all these expressions here and try to work it out and keep up to the linear order, the expressions for this spin connection up to linear order has this form. This is what I explained. Okay. And the other thing is that what is the sigma AB? So sigma AB is basically the spin matrix that basically appears under Lorentz transformation. Okay. So this is basically, this defines the spin of the particle, and this basically under Lorentz transformation, you know that like if there is some Lorentz parameter, which I think Subbu has explained, that lambda dot sigma, this is the same sigma here. Okay. Now what happens is that since we have written down our 1-pi effective action in momentum space, so we want to see what will be the consequence of this covariantation prescription, what I just described in coordinate space, in the momentum space. So for that, so okay, I have already copied it. So I want to see what will be the consequence of this term in the momentum space. So obviously, like say there is single derivative. So to start with, what happens? Okay, sorry. I'm not used to it. Okay. So what happens is that, like, suppose you have some delay of phi alpha single derivative. What we are doing is basically we are replacing by inverse BL bind and up to linear order. This is minus S A mu. And there is this covariant derivative part, which is d mu of the phi alpha, and the d mu expression is written here. So up to linear order in S and A, but you can see that due to this covariantization, what happens in momentum space? Say in momentum space, how this expression looks like. So momentum space, this expression will go like I PA into phi alpha. If we just do Fourier transform, then I am writing the same phi for momentum and coordinate space. So let me put the argument P. This is the coordinate space expression. This is the momentum space. Maybe I should write tilde, but it will complicate. So that, then how that will change? So then I have to write the Fourier transform of each of these variables, and you can see that effectively what this gives. So this basically tells us that, let me remove this I factor. So this will tell us that PA of phi alpha will basically translates to PA of phi alpha minus Q alpha beta. Let me write the polarization tensor for the mu gauge field with momentum K to phi beta, and then plus half of KB epsilon mu A minus K epsilon mu B times sigma AB alpha beta phi beta of P. So you can see that due to this covariantizations, the momentum of the finite energy particles shifts to a part which is this part, and this part basically is dependent on the polarizations of the photon as well as the graviton. Somehow the keynote is being offline. Okay.
What happened?
My keynote is again frozen. So now I think, yeah, it's online. Now it is, no, it's still frozen. Sorry. Okay. So what this is telling, that this covariantization procedure, like if you replace the ordinary derivative by covariant derivative, what you are doing is basically you are shifting your momentum of the particle by this amount of, by these terms. Okay. So, and what I'm denoting here is basically the epsilon mu, which is basically the photon polarization, which is basically is the, if you do a Fourier transform of the mu nu, that will be the term. And this epsilon mu A or any epsilon mu nu, that will denote the graviton polarization.
So Biswajit, one question.
Yes.
How do you know that this is a unique way of replacing this del alpha phi alpha by what you have written here? I mean, can there be other alternative choices?
Okay, like up to the, see what happens is that to do this, what I used is basically the gauge invariance and the general coordinate invariance. And for the gauge invariance and the general coordinate invariance, up to the linear order in K, this is the only way, like this is the only term which can appear in the covariantization procedure. Because you want that with respect to the soft graviton field, which is say epsilon mu nu, you want that under general coordinate transformation, like using this replacement, your action should be invariant if you replace epsilon mu nu plus say k mu xi nu plus k nu xi mu, your accent should be invariant. So if you demand that general quantity invariance, with this also the gauge invariance, say epsilon mu, polarization of the photon goes to some k mu lambda, then this is the most general way to covariantize the ordinary derivative to the covariant derivative.
Okay. Okay, one more related question, like, can you go the other way around? For example, starting from this general expression on the right-hand side, by taking a soft limit, can you go back to the left-hand side of the expression? Meaning, is there any way of taking a soft limit?
No, okay, here we are not even using the soft limit. So in a sense, soft limit means I am keeping the terms up to order which is linear in k, like up to, since I want to, one can keep up to other terms. Like in the single derivative, actually other terms also don't appear. As I can see, only linear in k terms, this is the only expressions, unless you want to keep more number of epsilons, more than 2, 3, or which will be important to study multiple. For single derivative, this is the most general expression of covariantization.
Okay.
Maybe I can add a comment. I mean, like if you consider, for example, fermions, then they are represented in the tangent space. Okay.
Right.
I mean, of course, other fields can also be made to go to tangent space, but fermions naturally live in tangent space.
Right.
So when you like construct the covariant derivative, it will have only the spin connection.
Right.
And then when you convert that covariant derivative to this dA, then you would add another EMU to the d mu, and that gives you the other term. So this is like in any theory of gravity, this is how you would define the covariant derivative, right?
Right. Okay. But if you have, say, two derivative, say you have, say, del A del B of phi alpha, then you have to multiply by A mu, E, B nu, and then in covariantation procedure, then d mu, d nu of phi alpha, right? But now, see, since this contains a vector index nu, so this, when you operate this covariant derivative d mu, it will contain also a Cristobal connection. Like we already have the spin connection and the gauge field part, and it, with this, it also contains a Cristobal connection. In a sense, like this expression will have the usual earlier expression, which is, say, A mu, EV nu, and then del mu phi alpha. So let me, sorry. Del mu delta, say, alpha beta plus, I'm using minus, sorry, minus q alpha beta mu, and then plus half of omega mu. I already have used AB, so let me use CD, and then alpha beta sigma CD, sorry, I'm extremely sorry. So alpha beta, with this you have a similar expression, which is del nu delta beta gamma minus q beta gamma mu. In some phi gamma, but with this you will have another contribution, which is gamma mu nu rho d rho phi alpha. You can write down that d rho in phi alpha other terms. So this contribution would be there. So you have to, now you think, now you see that you can write down, like, then you can translate to this thing. If there is two momentum, like if a function is quadratic in momentum, then basically you have to shift the two momentum to be like in a momentum space by this expression.
Biswajit?
Yes.
Did this not taking symmetrized derivatives, did it help you in any way in calculation? Because it's a bit less elegant in the sense that it will also give you non-universal terms which you discard because it's sub-subleading.
Right. So okay, means actually what happens is that I can take this to be symmetry.
Yeah. Because then you will only get universal terms naturally from this prescription, and because if you have a theory which you are minimally coupling to gravity, the theory in the flat limit, it will give you no information on how you should couple it to curvature.
Right.
So
what happens is that from here you will get also a curvature terms with a particular coupling.
Yeah,
but now you can add a general curvature dependence term with some arbitrary coupling, and then with this arbitrary coupling you add these two things and define a new coupling, and this will be your new non-minimal term.
Yeah, okay.
Means in that way you can combine, but I think it's better to work in a symmetric form. But since I'm not, I've actually since the Riemann tensor terms always affect the sub-leading order, and I don't want to study, so that's why I'm little lazy to symmetrize the expression.
Okay, sure. Okay.
So now with this understanding, so now what we need is that
Biswajit,
yes,
I just wanted to point out that it's already 4 o'clock, but we are going to give you 10 minutes extra.
Okay.
So just keep that in mind.
Okay, thank you.
So Ravi Teja is asking, hello.
Yes, I can hear.
Ravi Teja is asking, is it possible to just recap the arguments in the lecture so far in last 5 minutes? Can you recap the arguments in the lecture so far in last 5 minutes?
Okay. Thank you. I'll do that. So just let me draw two kind of diagrams which one have to compute to get the a single soft photon and soft graviton theorem. Then I will again recap the arguments. Okay. So I'll do that in 2-3 minutes and then I will recap. Thank you. So what we have to do that we have to derive two kind of diagrams. So what I want to do is that after this covariantization technique, like now you have a covariantized action, which I will show maybe in the next day. And from this covariantized action, now you can compute what will be the vertices and the propagators. So already the finite energy propagators you can compute from the even just after the gauge fixed action. Now to get the vertices for which corresponds to also the finite energy particles as well as the soft particle, that for that you need the covariantized action to derive the vertices. And what you only need is basically this gamma 3 vertices which I have written here, which basically takes care of the two finite energy particles and one soft particle. And the other, so this is the diagram where basically the soft particle connects to external leg. And this is basically the complement of the first kind of diagram. Complement of first kind. Okay. So why I am dividing by these two kind of things? Because you see, so this is Pi plus K. So why I am dividing by these two things? Because the first kind of diagram you can see contains a propagator with momentum Pi plus K. So this gives like 1 over Pi plus K whole square plus Mi square, right? And which if you use the on-cell condition of the particle I, then Pi square plus Mi square is 0. So what you will get is basically pi dot k, 2pi dot k. So you can see this diagram contains a 1 over the soft momentum, where k is the momentum of the soft particle. The next diagram, since it is attached, like the soft particle attached to some internal line, so this does not have any kind of this kind of soft, like any kind of propagator which can gives you 1 over momentum. So that is why I have divided two kind of diagram. The first kind of diagram, since it contains 1 over soft momenta, it start contributing at the leading order. But the next diagram, which does not contain such kind of propagators, it starts contributing only at the subleading order. It will not affect the leading order result. So in that way, basically what turns out that if we can compute these two sets of diagram and sum over all particles I, because this k graviton or photon attached to ith leg, one have to sum over all possibilities, basically drawing all such kind of diagrams. Then one can get the full amplitude, which is basically which contains n number of finite energy particles and one soft photon or graviton, and then try to write down this amplitude in terms of a endpoint amplitude which don't have this photon or graviton. So this will be the goal of the next lecture using this covariantization prescription. So now let me, yes.
So when the soft particle connects to the external leg, can't it connect using a 4-point vertex?
If you connect by a 4-point vertex, then this basically goes into the next diagram, because that does not contain a propagator which can give you 1 over momenta. Say for example, what you are telling is that, say, why not this kind of diagram is allowed, right? But you see, yes, if it has pi, it has pj, it has k, then this momentum is pi plus pj plus k, right? So what it gives the propagator, pi plus pj plus k whole square, plus say all the particles are same mass, m square, right? So one of them goes by on cell condition, but still you will have say pj square or say 2 pi dot pj, and then you have also order k term contained. But now k is like, since these terms are much bigger than the linear in k terms, so in the k expansion, this will give a finite result, and the k will go in the numerator in the expansion. So this cannot give a 1 over k term, right? So this kind of diagram are already included in this kind of vertex, which I have defined gamma tilde, which does not give a 1 over soft momenta factor. Is it understood? Parindam?
Sorry, I was muted. Yeah, it's understood. Thank you.
So one of the assumptions that we made, that the vertex does not contribute to 1 over k, or so this assumption is crucial here.
Yeah, this assumption is crucial here. Otherwise, this kind of diagram could have one have to include.
Okay. And presumably this breaks down in d equal to 4. Is that right?
I will show that in d equal to 4 this breaks down. Okay. Yeah, this is precisely the reason.
But sorry, how can the vertex factor contribute a 1 over? Why is this an assumption and not a?
Okay, so I think like if you consider a local theory, you can think that this is natural, right?
Yeah.
That one should not vertex. But see, we are starting from a UV theory or some theory, and we are computing a 1K effective action. But this effective action can have all kind of information. We don't know that the effective action have to be local or not.
I see.
Right.
Shubham, for example, if the UV theory or the 1K action is that of string theory, the vertex typically will be non-local, and they may contain such factor in principle.
I see. So you are saying that if I try to write down some Lagrangian, it can have something like some r square by k square. R is some Riemann tensor set, something like this sort of thing.
I mean, in principle, I mean, until we fully write down the Lagrangian, we don't know for sure.
I see.
But in principle, you can't rule them out apparently.
In 1K effective action, this term could appear. Though in usual the full action, whatever you have there, if you demand that your theory is local, this kind of terms you will not write down. But now when you integrate out all the quantum degrees of freedom and got a effective action, it is not sure that we will not get such kind of terms. And I will show actually in 4th dimension how such kind of terms could appear, and that will be problematic in our analysis.
I mean, like if you start off with a pure theory of gravity, say,
right,
then also you expect such things to happen?
Yeah, so let me show maybe in one diagram. So say I want to study force in usual Einstein gravity, say one effective vertex which has 4 scalar and 1 graviton. So at one loop order, this can contain a term which is say.
No, I'm saying pure gravity. So therefore there are no scalars, right?
Okay, so in pure gravity. Okay, in pure gravity, I'm not sure, but we can try. Okay, so in pure gravity, say, for example, you have, okay, so you have a diagram. So maybe it's becoming worse. So let me go to the next slide. So,
Biswajit, your screen is frozen again, I think.
Yeah. Next day I will now install.
Also, you have 1 minute left on your extra 10 minutes.
Okay. So I'll just finish by this comment. Maybe I will recap in the next lecture in the beginning. The request for the recap, I will recap in the next lecture, past lecture what I have done.
Is your iPad connected to the Wi-Fi?
Yeah, it was fluctuating. That's what happens. Now it's connected. Now I hope that it will work. Yeah. Sorry. Yes. So now suppose you have a graviton loop and suppose this diagram. Okay, so this is, you can think of as a part of 1 pi vertex with 5 gravitons. Right, this is at one loop level, this kind of diagrams will be there inside this 1 pi vertex. To get the 1 pi vertex, you have to analyze these diagrams also. Now let us try to understand that, like, what will be the structure. So this is say soft momentum K, and this was say P1, P2, P3, P4, and try to understand like how it will look like. So first of all, you see, so this is suppose loop momentum small l, and let me give this thing as P1 plus small l. This is P2 plus small l. This is P2 plus small l plus k, some kind of thing. So now this contains a set d to the power d l upon 2 pi whole to the power d, some 1 over l square, and from here there is some P1 dot l. You will have a P2 dot l after using on cell condition, and you even have a like P2 dot k plus l, and you will have a numerator factors, but the numerator factors, when you expand in k, the linear order will be independent of k, because there could be vertex which depends on only like p1 and p1, right? Say 2 p1, this vertex will be p1 mu 2 p1 mu p1 new kind of term. So the vertex factor up to x, like that will be order k to the power 0 plus some order k term. So let us only take care of the order k to the power 0 piece. Now you see that when the loop momentum integrated over all the region, but when the loop momentum turns out to be in the order of the external soft particles momentum k, and you fix d equal to 4, you see that you will have a 4 number of loop momentum in the numerator, and in the denominator you will have a 5 number of loop momentum. So it can basically go like, since you approximated the integral from omega like k to some other value, so it contains a 1 over k factor. even in 4 space-time dimension. Subhamda, is it?
Is the screen is frozen again?
Okay, but with this expression you can see, like this expression whatever is written,
right.
So you can see that it has how many number of loop momenta below is 5.
5, right.
But in the numerator, if you fix d to be 4, it's 4. Right, and basically if you analyze the integral from loop momentum greater than k, then this basically gives from the lower value of the integration limit 1 over k.
Some logarithmic thing.
So yeah, this is actually 1 over k, like since one part is in the denominator greater than above. So it is like dl upon L square.
Right.
Yeah.
Sorry. Yeah.
So in 4 space-time dimension, this could be a problem from the loop amplitudes.
So
okay,
I think
so let me stop. Yeah.
So I think one can say that in 4 dimension, any massless particle being integrated over will typically lead to a non-local 1PI effective vertex.
Right.
Okay, so I guess we have run over time. We need to start the next lecture on time as well.
Right.
So let us all thank Biswajit by unmuting yourself and clapping or using the clap button. Okay, so so we will pause the recording for now. In the break, if someone wants to ask any further question to Biswajit, please go ahead. Maybe Biswajit, you can, because Ravi asked, maybe you can just give him a summary of what was talked about today.
Okay.
Okay, so we come to the second lecture of the supergravity and the last lecture of the first day of ST4. So please, Subbu, go on.
Yeah, hi everyone. So I'll first do a recap of the first lecture, and then if there are some questions, we can take them and then we can continue. Okay. So first, what we studied is that Clifford algebra is defined by this relation. Okay. And this was this is interesting because if there are gamma matrices which satisfy this relation, then these matrices form a representation of the Lorentz algebra. Okay, and it can also be written this way by notation that we defined later. And we also defined the complete Clifford algebra, which is 1 gamma mu 1 mu 2 gamma mu 1 mu 2 mu 3 and gamma mu 1 to mu 4, okay, which are completely antisymmetric matrices, and mu 1 is less than so on to mu 4 to avoid repetitions. Okay, and now this set could also be written in terms of another set, which is 1 gamma mu 1 mu 2 gamma 5 gamma mu gamma. Okay, and when you count, if you use the first set or the second set, basically you are doing 4CR or 4C 4 minus R. Okay, I mean some of the terms are 4C 4 minus R, I guess, but doesn't matter. 4CR is equal to 4C 4 minus R, so that is 2 to the power 4, which is 16. Okay, and using this fact, we realize that these matrices span a vector space of 4 cross 4 complex matrices, and we defined this object M is equal to 1 M, which is summation A, MA, gamma A, and using the trace property of the complete Clifford algebra matrices, which is this trace gamma A, gamma B is 4 delta AB, we derived that MA is 1 over 4 trace gamma A. Okay, so now so these are the properties, and of course we know from here that sigma mu nu forms a representation of the Lorentz algebra, so we can define something that transforms under infinitesimal Lorentz transformations as minus lambda mu nu by 2, plus lambda mu nu by 2 sigma mu nu psi, okay, where the half factor is to avoid double counting, because sigma mu nu is an antisymmetric matrix, so you don't want to double count sigma 1 2 and sigma 2 1, let us say. So that is why this half factor. So this can also be written as lambda dot gamma by 4 times psi because of this relation. Okay. So this is the this is the basic Clifford algebra structure that we use, and it helped us in defining this spinor, which transforms in this way under Lorentz transformation. Okay. Are there any questions about this part? Okay. Let me continue. So given these matrices, we can construct bilinears. Okay. So of course there is one quantity which we are all familiar with, which can be used to construct a bilinear, and that is I psi dagger gamma 0. Okay. And this transforms in the opposite way under Lorentz transformation with a minus sign. Okay. I psi dagger 0 gamma dot lambda by 4, where gamma dot lambda means gamma mu nu lambda mu nu. Okay. And these are parameters of the Lorentz transformation. So this, for example, tells us that I psi dagger gamma 0 M psi is Lorentz invariant if M is Lorentz invariant. Okay. So this is useful because we want to construct Lorentz invariant actions. Okay. But then we defined a new object called the Majorana conjugate, which is psi bar psi transpose C. Okay. Now psi transpose C, which is psi bar, also transforms in the same way, okay, as the Dirac conjugate, which is I psi dagger gamma 0. Okay. And this matrix C was a matrix which exists in every dimension with the property that C gamma R transpose is minus TR C gamma R, where TR is plus or minus 1. And we had two matrices in 4 dimensions. So one was sigma 1, sigma 2, another was sigma 2, sigma 1. So this says T0 is equal to 1, T1 is equal to 1, this is T0 is equal to 1, T1 is equal to minus 1, and TR plus 2 is minus TR. Okay. So using that, you can get all the other T's. Okay. So this is in the product representation of gamma matrices. And we also discussed that given one representation, how to go to another representation, okay, which is for gamma prime R, which is S gamma R S dagger, we will have C prime, which is S star C S dagger. Okay. Because we are considering only Hermitian representation of gamma matrices, we will only consider similarity transformations, which are also unitary. Okay. So, and something to note is that C is also unitary. Okay. And S is also unitary. So now, so using these, we defined spinor indices, which basically psi bar alpha was C alpha beta psi beta, where psi beta were the indices of the spinor. Okay. Spinor psi. Okay. And then we derived two important properties, okay, of these spinors and their bilinear. So one is called Majorana flip. Okay. And that tells us psi bar gamma r chi is TR chi bar gamma r psi. Okay. So I will write a more general version of this, which I did not derive. which is if we have psi bar gamma R1 to gamma RP chi, then this is T0 to the power P minus 1 TR1 to TRP chi bar and then gamma matrices in the reverse order. Okay. This is also derived using the same way like this was derived. Basically, this is a number, so you can equate it to its transpose. Okay, and this T0 comes from the fact that because there are many C's, okay, you will have something like C gamma gamma transpose. This is gamma transpose times C gamma transpose. Okay. Once you do this one, okay, you will get, let's say, C T corresponding to this. Okay, I don't know how to write it. Okay, let's see T corresponding to this one. Okay, and then you will have gamma transpose C gamma. To convert this C to C transpose, we need T0. Okay, minus T0. So that is why this T0 to the power T minus 1. Okay, so this is more general form of Marana-Flip relation. So given any bilinear, which is like given product of these matrices, you can convert it into these bilinear with the spinors interchanged in the bilinear. Okay. Are there any questions? Okay. So another property that we derived was Fier's identity. I'll just write it in its final form, which we derived. And this is also probably the form that one can find in Peskin, for example. So chi psi bar is minus 1 over 4 psi bar chi minus 1 over 4 psi bar gamma mu chi gamma mu minus 1 over 4 psi bar gamma 5 plus 1 over 4 psi bar gamma phi gamma mu chi gamma phi gamma mu plus 1 over 8 psi bar gamma mu chi gamma. Okay. Now, if you use chiral spinors, okay, then many of these gamma phi's become redundant because when they act on specific spinors, they give either +1 or -1. Okay, and also we saw that the Fier's identity greatly simplifies. For example, chi L psi bar L is minus half psi bar L chi L PL plus 1 over 8 psi bar L gamma. Okay.
Quick question.
Yeah.
So if I remember correctly, and I'm not sure I do, Fier's, is it a single Fier's identity or are there multiple Fier's identities? I remember sort of there being like a lot of Fier's identities or something.
Yeah, I mean, okay. I mean, you are asking in supergravity, right? I mean, yeah, because I think in amplitudes there is some some quite different Fier's identity. But in supergravity, like people will write many things saying Fier's re-identity. For example, even in Friedman and Van Proen, okay. First they derived as delta alpha mu, delta beta nu kind of a thing, and then they do various combinations. Like for example, psi bar m1 chi, I don't know, phi bar m2 whatever, zeta, something like that. Okay. And then they do some Fier's rearrangement for this particular combination as well. Okay, but if you know this one, right, you can do any manipulation with Marana-Flip because like chi phi bar, you just use this. Okay, it's this. You just use this relation. It's the same Fier's rearrangement that you will get. Okay,
I see.
And if you want to,
so from this you can get all the other things that people call as Fier's identity.
Yeah. And in fact, if you look at like Mohap's lecture notes, which is also a reference that I shared, okay, which is also a classic reference for this modern supergravity. So in the appendix, they only give this Fier's rearrangement. And so basically people just use it in this form.
I see. Okay.
Okay. Yeah. Okay. So, all right. So this is the Fierce rearrangement for chi-L, and if we have chi-L and psi-R, then we have minus chi-L. Okay. So yeah, so it Fierce identity or Fierce rearrangement greatly simplifies when you have chiral spinors. Yeah. Are there any questions? So this finishes my recap.
Subbu, can you remind me why you are just focusing on d equals to 4? Is that for pedagogic reason or something else?
Yeah, for pedagogic reasons.
Okay.
Because like what I have observed is that supergravity or supersymmetric courses start with discussion of Clifford algebra in general dimensions, and basically if you have only a few lectures, you will get lost in that discussion.
Yeah.
Yeah. So, and also, I mean, all the work that I am familiar with or I have done is in like 4-dimensional supergravity, and the subject is extremely technical. Like, I mean, there is possibility that if I start speaking of 5-dimensional supergravity, I mean, not the basics, but suppose some details, then I might make a fool out of myself. So that is also there.
Yeah. Okay, fine.
Yeah. Okay. But basically, the techniques in these lectures should enable someone to do supergravity in any dimensions.
Yeah, sure.
I don't think more input is needed. Yeah. Okay. So now let us define Majorana spinor fermions, which was our goal throughout. So the demand is to find the simplest spinor in a given dimension, even in a given number of space-time dimensions. Okay, because you consider some space-time dimension, let's say 4 space-time dimensions, and you ask what is the simplest supergravity theory. That should be comprised out of the simplest spinor in that dimension. Okay, so that, and also later we will see that supersymmetry means you have some number of conserved charges, which are spinors, which are fermionic charges. Okay, and they would have the lowest number of components if you consider the minimal spinor in that dimension. So to go to a theory of supersymmetry with the lowest number of supercharges, you need to study what is the minimal spinor in that dimension. Okay. So that is why we did all this discussion. And if you see, sorry, yeah, okay, yeah, sorry, yeah. So if you see this slide, okay, then you saw that this Dirac conjugate and the Majorana conjugate, they transformed the same way under Lorentz transformations. Okay, that tells us that we can impose the condition that Dirac conjugate must be equal to the Majorana conjugate, and whatever spinor satisfies that condition, that must have lower number of components than the Dirac spinor. Okay, so that is what we will do. So the Majorana condition, we will phrase it as psi bar is equal to I psi dagger comma 0. Okay, this is the Majorana condition, and where psi bar is psi transpose 0. Okay, so now of course we know that if we take I psi dagger gamma 0, okay, and take another Hermitian conjugation, then we will get minus I gamma 0 dagger psi, and this will be I gamma 0 psi, because in a Hermitian representation gamma 0 is anti-Hermitian. Okay, so we get this. So if we have minus I gamma 0 I psi dagger gamma 0, then we should get back psi. Okay, so using this, you can get the property that psi is equal to minus I gamma 0 psi transpose C dagger, right? Basically, I'm just using this relation, and instead of Dirac conjugate, I am substituting the Majorana conjugate. Okay. And this is nothing but I gamma 0 C dagger psi star minus I. So this object, which is minus I gamma 0 C dagger psi star, this is called as psi C, okay, which is called as charge conjugate of the spin. Okay. There are some nice properties of the charge conjugate. Okay, it can be used to simplify computations of reality properties of the bilinears, but I won't cover them in these lectures because they are not necessary for these lectures. Okay, so psi is equal to psi C is also a way of defining the Majorana condition. Okay, it's either this or this. Okay, one or two called Majorana. Okay, so okay, so now what we need to do is that using the above, we can prove that psi star is nothing but minus IC gamma 0 psi. Okay, and if we use so this I am not going to do, but if we use the fact that psi star of star is psi, okay, this is a consistency condition in the sense that if we have placed some condition on the spinner, it might as well lead us back to psi when we take the complex conjugation twice. Okay, and once we impose that, that tells us that T1 is minus 1. Okay, so basically this comes from the fact that in the earlier expression we had gamma 0. Okay, and when we take C gamma 0 transpose, it involves T1. Okay, because gamma 0 is gamma matrix of rank 1. Okay, so that is why you get T1 is minus 1. Okay, and this tells us that in 4 dimensions we should restrict ourselves to C2. Okay, because remember in our earlier case we had C1 and C2 in 4 dimensions. Okay, and both of them had T0 as plus 1, and T1 was plus 1 for C1 and minus 1 for C2. So therefore, if we define Majorana conjugation using C2 and we equate it to its Dirac conjugate, that's a consistent condition. Okay, so we will use C2 from now on, and from now on, C means C2. So in general dimensions, this property translates to T0, T1. Okay, T0, T1 should be minus 1 for Majorana spinner condition, and also T1 has to be minus 1. I mean, T0 has to be plus 1, T1 has to be minus 1, basically. Okay, that means Majorana spinner, and there is some technical distinction between that and T0, T1 being minus 1 and T1 being plus 1. Okay, which is called as a pseudo Majorana spinner. Okay, but I won't cover this technicality. It only appears in 8 dimensions, and we won't discuss this in these lectures. Are there any questions? Okay, so these conditions they relate psi star and psi, and these conditions reduce the number of components by half. Okay, so Majorana spinners have 4 independent real components, let's say, real parameters. Okay, the spinner in a given representation need not really be real. Okay, but the number of real components parameterizing the spinner are 4 instead of 8 for the Dirac spinner. Okay, and you can see this by seeing that, you know, like we relate psi is equal to psi c. Okay, so that means and this relation is invariant under a C operation, so they are not really, you know, as many number of equations and so on. But later I will show an easier way of seeing that there are 2 components by showing that given a Weyl spinner, you can write a Mariner spinner using the Weyl spinner. Okay, so I leave that as the demonstration in these lectures because that is quicker to arrive at.
Subbu, just go back to the last slide.
Okay. Yeah.
A bit dumb. So this 1 and 2 conditions that you specified, right? Both are for Mariner condition. Both are true for any dimension, is it?
Yeah. I mean, yeah. Both are true for any dimension.
Any dimension. Yeah, for any dimension, even or odd, I can do that.
Yeah, I mean, there are dimensions where Mariner spinners don't exist, but the conditions are this. Yeah.
Both the conditions. Okay.
Yeah, in the sense that these conditions are consistent if T0 is +1 and T1 is -1.
Right.
So that won't happen in every dimension, but whenever it happens, it's the same equation.
Right. But those 2 are equivalent statements.
Yeah. So basically, those conditions are called Mariner condition, but strictly speaking, Mariner condition is those conditions plus this.
Okay. That makes sense.
So now they need not really be real, but there exists really real representations, which I won't show in these lectures. Where the Mariner spinners are real. Okay, but of course, if psi is real, then psi bar is purely imaginary. Okay, and so on. Because psi bar is I psi dagger gamma 0. And really real representations are also discussed in Van Proen in some appendix. And if people are interested, they can see that. Okay, and of course, I mean, in really real representations, Mariner spinners are real, but they can be considered in any representation, and that is the approach with which we have taken in these lectures. I mean, even though I introduced gamma matrices in like one representation, the way I did Mariner condition is independent of the representation, because even though you know the C matrices in product representation, you know from I see. 1 second. Yeah, so you know from this equation how to obtain C in any other representation. Okay, and then the Mariner conditions are defined using these C's. Okay, so therefore our discussion has been fairly general, and it should allow you to define Mariner spinner in any representation, and physics does not change because all these are just equivalent representations. Okay, and now many people here might be familiar with Dirac spinners and Weyl spinners. So something to note is that given a Dirac spinner, we can always construct 2 Mariner spinners by using psi plus psi c by 2 psi minus psi c by 2. Okay, basically you can see that this T1 is equal to -1 also implies psi c of C is equal to psi. Okay, so that tells you that both of these psi 1 and psi 2 satisfy the condition psi 1 C is psi 1, psi 2 C is psi. Okay, and C we have chosen to be C2, so T1 is -1. Okay, so everything is consistent. So given a Dirac spinner, you can always define 2 Mariner spinners. Okay, so suppose someone tells you there is some supersymmetric theory with a Dirac spinor charge. Okay, that is a supersymmetric theory with 2 Majorana charges. So that is why you can just count supersymmetry by using Majorana spinors, which is a minimal spinor in 4 dimensions. Okay, and now
a quick question. Quick question.
Yeah.
So the like how the Majorana conjugate is defined for any spinor, and only for Majorana spinors it's the same as the Dirac conjugate.
Yeah.
The charge conjugate is also defined for any spinor, or is it only defined for Majorana?
Yeah, I mean, I have not studied it for every spinor, but I think it is defined for any spinor. Yeah.
I see. Okay. So
I mean,
if
naively, yeah, like if you look at Friedman and Van Proyen, if you look at like the discussion of how like charge conjugation can be used to see reality properties of like bilinears, that is general. That does not involve Majorana spinor condition. But if you use Majorana spinor condition, it is extremely simple. Like it will be simplified a great deal.
Right. So and also naively, like if you were to mode expand a Dirac spinor and see what would correspond to an electron or a positron, does the charge conjugation, do they sort of mix these? I mean, is that why it's called a charge conjugation?
Like charge here, like it involves psi star, right? And basically in the mode expansion, when you go from e to the power ip dot x to e to the power minus ip dot x, that is when you have this particle to antiparticle mapping. So yeah, it does the same thing. Yeah.
Subbu, can you just repeat the supersymmetry counting argument that you just gave?
Okay, I'll do it later in detail also. I mean, shortly after. What I'm saying is that given a Dirac spinor, okay, you can define 2 Majorana spinors. So this is Dirac, okay, and these are Majorana spinors, okay.
Right.
So the advantage is that if you have a theory with like 1 Dirac spinor supercharge, okay, which is like a conserved charge, okay, in that theory, then you can say that there are 2 Majorana charges by using this, okay, because if the charge is conserved, then psi plus psi c is also conserved, right? I mean, that q plus qc is also conserved. So you can construct 2 charges, and usually you count the symmetry, the amount of symmetry using the charges, okay, because charges are also generators of the algebra.
Right. And so that's why you can just directly count the number of Majorana spinors.
Yeah. So now people are also familiar with Weyl spinors. Okay. Now given a Weyl spinor, one can define Majorana spinor by using this condition. Okay, and this clearly satisfies the Majorana condition. And of course, conversely, we can also define PL chi.
Sorry. Just a bit confused. So psi 2c is psi 2 or minus psi 2?
Psi 2, because like psi 2c is. Oh, I see. I think I missed an I. Yeah. Okay.
Okay.
Yeah. Thanks. Yeah. So now, okay. So now we can also define this chi L and chi R, okay, which are Weyl spinors. Now you might think we had 1 Majorana spinor but 2 Weyl spinors, okay. But because of the Majorana condition, you can derive that chi L and chi R are not independent, okay. They are related by chi bar L is I chi R dagger gamma 0. And this relation we will use later also, okay. So, and so this I leave as an exercise, derive this from Majorana spinor condition, okay. And yeah, so this I leave as an exercise, and basically this tells us that we know that Weyl spinors have 2 complex degrees of freedom or 4 real degrees of freedom, and since they have a 1-to-1 mapping, Majorana spinors also have 4 independent degrees of freedom. Okay, is that okay? Okay.
Yes.
So now Weyl spinners are also, minimal spinners in this dimension. So one can, these two descriptions are equivalent. I mean, you can describe your theory in terms of Weyl spinners, or you can describe your theory in terms of Marana spinners. I mean, in the sense that all these discussions are not about the action as such, but about how many number of symmetries we have and so on. Okay. So if you have like one Weyl spinner charge, that is equivalent to having one Marana spinner charge, which is conserved. Okay. So therefore, like there are two formulations of supersymmetry. So one is called 2-component formulation, another is called 4-component formulation. So 4-component formulation concentrates on the Marana spinner, and we will use 4-component formulation. Okay. And in superspace literature, it is more common to use 2-component formulation, but in these lectures, we will not do superspace at all because we'll go in a completely different direction.
So the counting argument that you are giving, that also goes to for the Weyl spinners, right?
Counting.
Supersymmetry counting.
Yeah, sure. Because
same will go.
Same will go, because Dirac spinner is also made out of like 2 Weyl spinners, which we all know. So therefore, if you have like one Dirac spinner charge, that is like having 2 Weyl spinner charges.
Right.
Yeah. Okay. So with this, let us start our discussion on supersymmetry. This discussion is geared towards understanding supergravity, so I won't be the most general in this discussion, but I hope that people know that supersymmetry, okay, I hope people know that there is something called as Coleman-Mandula theorem, which says that if you have if you want an extension of the Poincare algebra where like the internal symmetries or where the bosonic symmetries also have a non-trivial commutation with the Poincare algebra, then that is not consistent with relativistic quantum field theory with some minimum number of assumptions. Okay, so we won't discuss this theorem here, but we will use a successor of this theorem called HLS theorem later. But basically note that if you have a fermionic symmetry on the other hand, it is always it always will have a non-trivial commutation with Poincare algebra, because a fermion by definition transforms under Lorentz transformation in a particular way. Okay, so if a fermion charge transforms in a particular way under Lorentz transformation, then with the Lorentz transformation generators, it can't have a zero commutator, right? Because action of symmetries on the charges are given by commutators, okay, or by Poisson brackets in the classical theory. Okay, so therefore, a fermionic symmetry must always come attached to the Poincare algebra, okay, and that is supersymmetry. So basically, supersymmetry is a theory where the transformation parameter is a fermion, okay, and by Noether's theorem, the conserved current will also be a fermion, or the conserved charge will also be a fermion, okay, and because it's a fermion, it is an extension of the Poincare algebra. Okay. So now we introduce some notation. Okay, we say that Qi are Majorana spiners and they go from runs from 1 to n. Okay, it's Gaussian. So when we say n is equal to 1 supersymmetry or n is equal to 2 supersymmetry and so on, what we mean is that there are that many number of Majorana spinner charges, okay, which are conserved. And I hope everyone knows that conserved charges also generate the algebra under Poisson bracket, okay, or in the quantum picture on the commutation relations. Okay. So now this terminology, however, does not naturally generalize to higher dimensions. Okay, because if I say n is equal to 2 SUSY, right? So this means that two Majorana spinners in 4 dimensions, right? 2 Majorana spinor charges for 4 dimensions. In some higher dimensions, there may not even be a Majorana spinor, or the Majorana spinor in that dimension might have different number of components and so on. Okay, so this nomenclature does not naturally generalize to higher dimensions. Okay, but there is an alternate way of saying this. You could speak of SU-C with 4, 8, 12, 16, etc. supercharges. Okay. This nomenclature will naturally generalize in the sense that supersymmetry with, let's say, 8 conserved charges in 5 dimensions will be related to supersymmetry which has 8 conserved charges in 4 dimensions and so on. Okay. So people use this nomenclature alternatively whenever they want to address a specific thing. Okay. So this is n is equal to 1, n is equal to 2, n is equal to 3, and so on. Okay. And yeah, so let us write the supersymmetry algebra. Okay. So SU-C algebra, of course, has the Poincare algebra, which I will not write. Okay.
Subbu?
Yeah, Mrutyunjay has a question.
Yeah, so there's a question in the chat. So let me read it. What are the assumptions about the manifold in Coleman-Mandula theorem? Does it work only for Minkowski space with Poincare symmetry? If so, what are the results for the other curved manifolds?
Yeah, I think it worked. It was done in with Poincare symmetry. I don't know what is the relation, what are the results for other curved manifolds. If someone knows, maybe they can say something.
As far as I know, I think one of the assumptions of the Coleman-Mandula theorem is that they require an S matrix, well-defined S matrix, and that is so again that ties down to the fact that for De Sitter and ADS, that is where the problem is.
Yeah, but I was thinking, like, what if you have some other asymptotically flat space-time? Like, I don't know if they have done for curved backgrounds
also. So the assumption requires a well-defined IR finite S matrix. So that will work for any asymptotically flat space-time, right?
Yeah.
Yeah, I think this is true for any asymptotically flat space-time.
Yeah, possible. Yeah. I mean, it's been some time since I have studied Coleman-Mandula theorem. Yeah, it's possible.
I mean,
it is also derived. It was also derived for 4 dimensions, as far as I know.
That probably can be generalized at least in the higher dimensions.
Yeah, I think so.
I definitely remember seeing it in somewhere. But for curved manifolds, I think, I mean, because Coleman-Mandula actually specifically talks about the symmetries of the S matrices. So I think for curved manifolds, I mean, either one will need to cast the symmetry of the theory in a different language, because S matrix is, if it is no longer definable, then what does it mean to talk about symmetries of S matrices?
Yeah.
Probably one can think about if the manifold has some isometry, then probably one can try to see if there is no S matrix in the space, like for example De Sitter, then it's not clear what does it even mean.
Yeah. I mean, maybe we can discuss these things on Slack, because these are not like directly relevant to the lectures, like defining amplitudes in the space-time. So maybe on Slack we can discuss. Is that okay?
Yeah, I think so. Please go on.
Okay.
Just Lata has a question. Can you just start?
Yeah, sure. Yeah.
You can unmute.
Yeah. Sorry, this is the basics of supersymmetry. So did you say that any n is allowed in all dimensions?
Okay, no, but I didn't speak of any restrictions in all dimensions. So basically what happens is that if you take, let us say, more than n is equal to 8 gravity in 8 supersymmetry in 4 dimensions, then you will know that, you will see that there will be higher spin objects in the representation theory. And that is why they are not considered, because, if it's a unitary theory, then higher spin fields won't appear in any interaction term.
Can I make a comment? Like, if suppose you are studying only massive representations and trying to study only massive theory, then there could be higher spin particles, and one can allow n greater than 8 even in 4 dimension.
Okay, maybe. I mean, but you know, like, I mean, because if you have, like, let's say n is equal to 8, I see. Yeah.
Sorry, massive higher spins, I don't understand. I mean, isn't it ruled out by Weinberg-Witten theorem?
I think only the massless, right? Massless higher spin particles have to be free. It cannot interact. Massive can be there, because in string theory also one have massive.
Yeah, but string theory is not a quantum field theory, right?
No, also
okay. In quantum field theory, if you think, then n equal to 4 you can go, not beyond even 4.
Yeah, because it has, I mean, if it's a local interaction, or the interaction vertices are local.
No. Okay. Biswajit, not like that. I think what he meant, like string theory is not a quantum field theory. Like n is equal to 8 is a perfectly well-defined supergravity theory.
Right.
Yeah. So, but I think what he means is that it is not a quantum field theory in the sense how you construct amplitudes and so on.
Okay.
I mean, n is equal to 8 supergravity has issues, like we don't know whether it's UV finite and so on. But like, you know, you can quantize it using rules of, I don't know. It's like a quantum field theory, but you can treat it like a quantum field theory. Yeah.
Okay.
But basically you can show that n is equal to 8 supergravity is the maximal supergravity in 4 dimensions. Okay, because after that you will necessarily have higher spin particles, and they are overruled. Massive representations I'm not sure of, because the way massive representations are constructed in like supergravity is quite indirect. So I don't yet understand. Maybe we can discuss later.
Okay.
Yeah.
So, what did you say about this 4-8 with n being 1, 2? Can you repeat the argument again?
So if there is one Majorana spinor conserved charge, it has 4 components. So there are 4 supercharges.
Okay. So for n equal to 8, there will be 32 supercharges. Is that right?
Yeah.
Okay.
And that is the maximal supersymmetry in 4 dimensions. And it's the same as maximal supersymmetry in any dimension. Like maximal supersymmetry in 11 dimensions has 1, n is equal to 1. And after 11 dimensions, if you consider any supersymmetric theory, it will have higher spin particles. So we won't, I mean, it will lead to higher spin particles in 4 dimensions. So we won't consider
that. Maybe we can discuss this later also. But how do you do this counting that, like you said, in 11 dimension, you can only have n equal to 1 supercharge?
Okay, basically you consider the spinor, okay, which is let's say the gravitino, okay, and graviton, okay, and you see by dimensional reduction what sorts of fields will appear in 4 dimensions.
Okay.
So yeah.
Okay, thanks.
Yeah. Okay. Okay, so let me continue. So SUSY algebra is defined this way. So this could also have, I mean, SUSY algebra in some other commutators can also have what is called as a central charge term, but I will discuss later when we go to supergravity why I am not discussing the central charge terms in these lectures. Okay, so this is the supersymmetry algebra. Basically, Q bar closest to translations. Okay, I should write beam you upstairs. Okay. So this is the supersymmetry algebra. So now what we will do is, these are Majorana spinors. Okay, so to study representations of supersymmetry, it is useful to go to the Weyl representation. I know it's annoying because we are like switching between 2 descriptions, but that is how it is. So what we will do is we will construct chiral projections of Majorana spinors, okay, which is ERQI and Q lower I is PLQI. Okay. And just like how I discussed earlier, they are not independent, right? Q bar I is related to I, QI dagger, okay, which I described earlier, that when you take chiral projections of Marana spinors, you have Weyl spinors, but they're not independent of each other. Okay. So this is that relation. Marana conjugation of one is equal to Dirac conjugate of the other. Okay. So now using this and applying chiral projectors on this SUSY algebra, we get Qi Q bar j is minus half PL gamma mu. Okay. So the other one is not independent, okay, which has Q upper I and Q bar lower j. Okay, and so we won't consider it separately. So this can be derived using the relation written earlier. So maybe I can copy it for comparison. Okay, I don't know how to move it, but let it be. Yeah. So basically, this was the algebra that we had earlier. Okay, and we have this now. Basically, what we have done is we have applied this chiral projectors, which is PR and PL. Okay, and because we have a gamma mu here, it is appropriate to multiply by PR on one side and PL on the other side. Because PL, when it goes through gamma mu, it will become PR, and PR square is 1. Okay, so this is what you get. Okay, and of course, Q lower I anti-commutator with Q lower j is 0 because PL PR is 0. Okay, now using the relation above, which is that Q bar I is I Q I dagger gamma 0, we can further simplify it as QI Qj dagger is equal to okay. So this is the relation, and of course, I mean, I'm not doing the step because I think everyone can do it. It's just that you just multiply by an I and multiply by gamma 0. Gamma 0 square is minus 1, so therefore you have to multiply. You still get the same sign. So this has IQJ dagger gamma 0. Okay. So you have to multiply by minus I, which would make it plus I, but gamma 0 also you have to multiply, and yeah. So and gamma 0 square here will give minus 1. Okay, so that will give you this relation. Okay, and so now what we can do is we will use the Weyl representation. Okay, and also we will define a notation which is very annoying, but this notation is followed, which is we will define this. Okay, so earlier we had Qj whole dagger. Okay, now we have Qj whole dagger is equal to Q dagger j. It's a very annoying notation, but basically this is there so that when you write delta ij, you can write delta ij appropriately. Okay, and index contractions become simpler. Does someone have a question?
Yeah, I have a question.
Yeah.
So, what do you exactly mean by supersymmetry? Like, what do these supercharges do? Like, trying to understand it. Like you have a U1 charge that generates, like, suppose Gauge transformation, right? So what do these superchargers that you've constructed? What do they do?
So what superchargers do is that they mix bosonic states with fermionic states. Like if you add supercharge on a state with some mass and some momentum, okay, then you will get another fermionic state with the same mass, okay, and that can be seen by the fact that P mu, I don't know if I wrote it earlier, P mu Qi alpha is 0. Okay. So we know two facts. One is that it commutes with momentum, so it won't change the momentum. Okay. Another thing is that it is a spinner, so it will change the spin of that state. Okay. So therefore, it gives you another spinner, another particle, which is either a, if this state is a boson, that is a fermion, and vice versa, but with the same mass. Is that okay?
Yeah.
Okay. Yeah. So that was the.
Can you explain that notation a bit more? This Qj dagger is equal to Q dagger J.
Yeah.
Is this the definition you are taking, or I mean, how do you define Q dagger and then take J?
Yeah, it is like, I don't know, like you could define it, for example, like some AJ, I wouldn't mind. It's some new object. Okay.
Okay.
So
But that is taking the dagger of Qj.
Yeah.
Okay.
It's a definition because, like here, I and J both were in the subscript, right? So I had to write this awkward delta Ij. Okay? Mm-hmm. And when this happens, like index raising, lowering becomes a bit annoying, right? So therefore, we define something with upper index so that index raising and lowering will make sense.
Okay, thanks.
Also, one more thing is that, when we go later in like extended supergravity, which is like supergravity with more than one supersymmetry, then there will be some internal symmetries called as R symmetries, which will mix these charges, okay? And if like this transforms in one representation, this transforms in the conjugate representation, the Hermitian conjugate. So it makes sense to give it like an upper index so that the SUN manipulations are simpler. Okay?
Yeah.
Okay. So now, all of this can be written in Weyl representations, okay, where gamma mu was 0, sigma mu, sigma bar mu 0. Okay. So I won't do it. I won't do every step, okay, but I'm sure everyone can derive this. Okay. So basically, in the left, I have done almost nothing because in the Weyl representation, we already had the chiral projections. Okay, so they just carry these lower and upper indices. Okay, so but the subscript quantum, okay, that tells that we have multiplied the commutator with an imaginary I. Okay, because so far what we were discussing was really the Poisson bracket of the generators. Okay. Like if you have like a classically supersymmetric invariant action, then what is the Poisson bracket satisfied by the SUSY generators? But this is the quantum anti-commutator. Okay. And
can I ask a question? Like classically, can you think of really some fermions or supersymmetry so that you start with Poisson and quantized it by some anti-commutator?
This is like the formal definition of classical limit of any fermion, right? Okay, like if you have like the fermionic action, like let's say some electron, you can have the action for the electron, right? Given the action, you can compute the Poisson bracket for the charges. Okay. If let's say it has U1 symmetry or something. Okay. But then when you go to the quantum theory, it becomes the commutator. Okay? Like when you take the Poisson bracket, it will go to the commutator of those charges. Okay. If you let's say if you have some SUN symmetry, okay, some non-abelian symmetry, the Poisson bracket of the charges in the classical theory will become commutator brackets in the quantum theory. But just like how there is no classical electron, In a similar way, there is no classical theory of supersymmetry in the sense that where the fermions also are classical. Fermions are quantum, but when we mean classical supergravity, what we mean is that you take a supergravity theory and you consider only the bosonic sector. Okay? So I will come to that later.
Okay. Thank you.
I mean, I will initially use a more broader sense of the word when I mean classical. I mean in the sense that in the Lagrangian description, where classical fermions have Grassmann valued objects, but they should not be thought of as physical classical quantities. And I think, the way you are describing in your soft theorem lectures about how you can construct coherent states of soft gravitons and consider a graviton radiation, okay, that won't happen for some spinor particle. Okay, let's say gravity, no, because spinners can't form a coherent state with large number of spinners because of Pauli's exclusion principle.
Okay.
Yeah. And Ji is given by half epsilon I Jk and Jk. Okay. So we need this. So now with these anti-commutators and commutators, let us try to understand massless representations of supersymmetry. Okay. Now, obviously, all these representations are in quantum field theory. Okay, and in quantum field theory, we know that we can define a standard momentum k bar mu, which is for massless particles, which is 0, 0, k. Okay, and if you start with this standard momentum, you can go to any other momentum by use of a Lorentz transformation. Okay, so you can study all the other symmetries in this standard momentum and then do a Lorentz transformation to go to some other frame. Okay, so that is what we will do. So now, if you consider the action of the supersymmetry,
so is there any specific advantage of going from Majorana SUSY algebra in terms of Majorana spinor to this Weil spinor? Any specific
in what we are going to do, like we are
going to do there,
we will see that this when you write these alpha beta indices, like when you take them for specific values q1 and q2, okay, and you take this momentum which is like k00 k, then you will see that one of them will act trivially on the Hilbert space and other one will give creation and annihilation operators. Okay?
Okay.
So it will become a process of quantizing simple harmonic oscillators or constructing a Fock space, which we are familiar with. Whereas in 4-component notation, it will look a bit more complicated.
Okay.
Yeah. So now, if we consider the action of the algebra on such states, okay, then people can work it out and find that this will become okay. So this is the algebra. Well, this k is the momentum, okay, and 1 and sigma 3 is intuitive because we had sigma bar mu p mu, and k is only there for sigma 0 and sigma 3. Okay, so that gave you this. So now, if we study further, if we just take the different components, okay, we will see that qi1, q dagger j1 is 0. Okay, which you can see here. Right. So if you take qi1 and okay, this would be q dagger. Okay, if you take q dagger j1, okay, then you will have 1 second. Yeah, then you will have 1 plus sigma 3, right? And 1 is this, and sigma 3 is 1 0 0 minus 1. Okay, so okay, 1 second. Okay, maybe this is minus. So let's keep that as a question mark. Okay, I'm getting a bit confused, but okay. So, but basically one of these components is 2 and the other component is 0. Okay, so for the other component, we will have a trivial anti-commutation. Okay, and for this component, for the component which is not that, we will have QI2, dagger J2, K delta. Okay. Basically, it doesn't matter for us like what is, whether one is the one which has this commutator or this commutator. Okay. The fact, what matters for us is that one of them has this trivial anti-commutator and another one has this non-trivial anti-commutator. Okay. And that I think it's clear from whatever we did in the previous slide. Okay. So now, suppose you are in a unitary theory and you consider this relation. Okay. Then you have some state which is, let's say, k bar h, okay, where k bar is our standard momentum and h is some other symmetry, like maybe helicity. And we consider, let's say, qi1, q dagger i1. Okay, I don't use summation convention in this expression. Okay, and k bar h. Suppose we consider this. Okay, now this must be 0 because of this anti-commutation. Okay, but that implies that qi1 and q dagger i1 act trivially on the Hilbert space, right? Because in a unitary theory, the norm of the states are positive. Okay, and here what is happening is that you have this expression for this particular choice. Okay, will be sum of norm of two states. Okay, and that can't go to 0 because both of them are positive. Okay, so therefore qi1 and q dagger i1 act trivially on the Hilbert space. Okay, whereas qi2 and q dagger j2 act non-trivially. Okay, so these form harmonic oscillator.
So by acting trivially, do you mean that they annihilate the state?
Yeah, yeah. Okay. So qi2, q dagger j2 is k delta ij. Okay. So whenever we say acting trivially, usually it means identity, but here these are generators. So it's like whatever is their action, it's like that state plus the action of the generator. So that's why for annihilation we call it acting trivial. Okay. So now, so these form creation and annihilation operators. Okay. So qi2 and q dagger i2, which is also qi2 dagger. Okay. So that so they form creation and annihilation operators. Okay, and so this is the creation operator. This is the annihilation operator. Okay. Now we can construct the Hilbert space by choosing a number of these objects. Okay, which is, let's say, q dagger i1 2, q dagger i2 2, so on up to q dagger im2. This can be the Fock space. Okay, but of course these are anti-commuting objects. Okay, q dagger with itself anti-commutes. Therefore, this object has to be antisymmetric in the indices I1 to IM. Okay, and by the relation J3 q dagger I2 is equal to minus half q dagger I2, okay, which we can derive from the relation we had earlier, which is this relation. Okay, from that relation, we can show that q dagger I2 lowers the helicity by half. Okay, this is the answer to an earlier question about what they do to states. Okay, so they change the state, the helicity of the state by half. So therefore, they're converting bosons to fermions and vice versa. So we give a notation which is I1, I2, IM, okay, K bar, H0 minus M by 2. Okay, sorry. And this is a state, ket vector, which is Q dagger I12, Q dagger I22, Q dagger. Okay, and of course, M can run from, I mean, if M is 0, then of course we have the vacuum. Okay, so M can run from 0 to N. Okay, because all these indices, I1, etc., okay, they run from 1 to N. Okay, and if you have a completely antisymmetric object, okay, of these indices, then you can't have it with more indices than the dimension of this I. Okay, because then some index will repeat and that will be 0. Okay, so these are the states. Do people have, I mean, are there any questions?
Can you repeat the last sentence that you made somehow?
Okay, what I mean is that suppose, so I runs from 1 to curly N, right? Okay, right. Which I'm writing in this corner. Okay, so now suppose you want to construct a tensor, okay, which is, let's say, IN plus 1. Okay, right. This, which is completely antisymmetric in all these indices. Okay, then this will be identically 0. Okay, because one of them has to have to repeat. Is that okay?
Yes.
Okay. Yeah. So that tells us that we have this structure. Okay, and of course, because these are antisymmetric tensors, just like how we did with the complete Clifford algebra earlier, we know the counting using combinations. Okay, so if we want to know how many number of these states are, then we have M is equal to 0 to N, NCM. Okay, these are the number of states that we have finally. Okay, so going from vacuum to the state with the highest number of Q daggers, and this is 2 to the power n. Further, we know something more about combinations, which is that if we sum even M or if we sum odd M, then the combinations are equal. Okay, and they're half of this value. Okay. So this tells us that, okay, so this will slowly appear, the equation. So this tells us that the number of bosonic and fermionic states are equal, right? Because Q dagger is changing the helicity by half, right? Decreasing the helicity by half. So if you had a boson at one level, you have fermion at the next level and boson at the level after, and so on. Okay. So for even M and odd M, you go from bosons to fermions or vice versa. So the number of fermions is equal to number of bosons. And although I have proved it only for massless representations, this is a general property and it can be proven without going into massless or massive case as well. But I just refrained from doing that in these lectures. Okay. All right. Right. So now there is a further condition, which is that we know that if a theory is a relativistic quantum field theory, then it has CPT invariance. Okay. So therefore, these states must also have their CPT conjugates inside the same representation. Okay. So that tells us that there are states with K bar minus H naught. Okay, maybe I should have used the notation. Okay, I used it, but I didn't explain. So for the minimum one with, for the one with no Q daggers, we call it H naught. The helicity as H naught. Okay, and its CPT conjugate would be K bar minus H naught. Okay, and then they can successively act with QI2s. Okay, and they raise the helicity. and that also will give us some number of states. Okay. So, I mean, the same number of states. So that doubles the number of states in the representation. Okay. So we can consider a few examples and then this might become clear. Okay, what we are doing.
Can I make a statement? Like, this doubling may be always not needed, right? Because it may happen that always their CPT invariant state is present.
Yeah, true. Yeah, the multiplet might also be self-conjugate. So yeah, I mean, I was just overlooking that detail. Yeah, that is
okay. Okay.
Yeah, true. Yeah. So a multiplet will basically have 2 to the power n or 2 to the power 2. I mean, or 2 to the power n plus the or 2 to the power 2n. Okay, number of states, but it depends on whether it is self-conjugate, and that can also be counted. Okay, so basically we need if it is self-conjugate, then h bar minus n by 2 will be equal to h0 minus n over 2 will be equal to minus h0. Okay, that is when it will be self-conjugate. So that will tell us 2h0 is n over 2. Okay. So if h0 is n over 4, okay, then the multiplet is self-conjugate. Okay. So for n greater than 1, this can happen. For n is equal to 2 and so on. Okay. So let us consider a few examples. Okay. So suppose I have n is equal to 1 and h0 is equal to 0. Okay. Then h value can be minus 1, 0, and 1. Okay. And the number of states I write below. Okay. So we start with h0 is equal to 0. Okay. And okay, why did I write minus 1? Sorry, minus half. Okay. So we start with the state with h0 is equal to 0, and so that is 1. Okay, there is one scalar, and when we act by a Q dagger, that will give 1 helicity minus half, and we can consider h0 is equal to 1, which is like CPT conjugate, and act by Q, which will give you the CPT conjugate state. So there are totally 2 bosonic degrees of freedom and 2 fermionic degrees of freedom. So this corresponds to us. Yeah, 1 sec. Yeah, I'll listen to it. So this is a fermion, which is let's say spin half, okay, and 2 scalars, let's say phi and something else, zeta. Okay, 2 scalars. Okay, Debbie, yeah.
Yeah. So you just wrote down this relation h naught equal to n by 4, right?
Yeah, yeah.
So that is when it is saturated. So for n equal to 8 supergravity theory, can I say that maximal supergravity is self conjugate? I mean, that's right.
I didn't get you. Sorry.
So for maximal supergravity, when n is equal to 8,
yeah,
can I say that it's
the multiplet is the multiplet is self-conjugate. Yeah.
And that's the only theory where you have self-conjugation?
No.
Or do you have for okay?
No. Like, I mean, you're saying the supergravity multiplet, right? Yeah. For supergravity multiplet, that is correct. But then there are other multiplets for which will be self-conjugate. Like, for example, in n is equal to 4, right? The vector multiplet is self-conjugate. With x0 is equal to 1. Yeah.
Okay. Thank you.
Yeah, sure. Okay, so this is the scalar multiplet in n is equal to 1. Okay, and n is equal to 1, h0 is equal to half. So just to make clear, like there is a typo in my notes. I have written this minus half and half as 1 and minus 1, which is not correct. Okay, so we can consider this multiplet, which is h0 is equal to half. Okay, that has minus 1. So now, the way I am writing it is that after the minimum one, which is like half, there is one step in n is equal to 1. Okay, because you can only consider one rank antisymmetric tensor in n is equal to 1. Okay, so half there is 1. Okay, I see. Did I do something here? Okay, I think I did something wrong here, which is that, let's see. Okay, so for n is equal to 1, let us consider h naught is equal to half. Then this will give us h naught is equal to 0, and we will get h naught is equal to minus half, will give us h naught is equal to 0. So this should be the same multiplet as the multiplet before. So yeah. Okay, I don't understand this, but I'll clarify it in the next lecture. Okay, but but we can consider n is equal to 1, h0 is equal to 1. Okay, then we can have h0 is equal to 1, and h0 minus half will be half. Okay, and minus h0 is minus 1, and minus h0 plus half is minus half. Okay, in my notes, I might have added helicity instead of subtraction, which is why I think I goofed up. So this is the multiplet for n is equal to 1, h0 is equal to 1. This is called as the vector multiplet. Okay, it has one spin half particle and one spin 1 particle, which is a gauge field. Okay, because it's massless. Okay, yeah. And you can have n is equal to 1, h0 is equal to 3 by 2. So h0 is equal to 3 by 2. h0 minus half is 1. Okay. So this multiplet will have, one spin 3 half and one spin 1. But this multiplet is not does not admit any consistent interaction term. I don't know proof for this, okay, but this happens to be true. But I mean, I know how to say it indirectly, in the sense that if there is a massless spin 3 by 2, then it will be a spinner gauge field. Okay, let's say psi mu alpha. And if there is a spinner gauge field which is gauged, then it becomes supersymmetry, and there must be a spin 2 state. So, but I don't know how to rigorously prove this. So the next multiplet is the supergravity multiplet, where you consider n is equal to 1, h0 is equal to 2, right? So you will have 2, and 2 minus half is 3 by 2, and you will have minus 2. Minus 2 plus half is minus 3 by 2, so 1. Okay, this is h, this is the number. So this has one spin 2 particle, which is the graviton, and one spin 3 by 2 particle, which is the gravitino. Okay. So this is a supergravity theory, and we will see later how to construct these theories. Okay. So this is for n is equal to 1. Okay. So if we go more than this, then obviously we will have higher spin particles, so we won't consider that case. And similarly, in n is equal to 2, okay, there is a vector multiplet. I sort of doubt all my counting now in the notes, but they will be fixed by tomorrow morning. Okay, and there is a hypermultiplet. So hypermultiplet has 4 scalars and a doublet of fermions. I think this counting is correct. Okay. And vector multiplet has a gauge field, mu, and a doublet of 2 scalars, okay, and a doublet of fermions, okay, and there is the gravity multiplet, okay, and this has okay. So maybe I should mention, okay, yeah, I think this will come now. So there is a gravity multiplet where there is one spin 1 gauge field. Okay, let me call it mu, which is called graviphoton. And there is doublet of gravitinos. Okay, and graviton. Okay, So if you count, you will find that the degrees of freedom match between bosonic and fermionic states. Okay, are there any questions?
Yeah, I have a question.
Yeah.
So till now, all the particles are massless, right?
Yeah.
Oh. And like, what is the vacuum state we are considering here?
Oh, in this representation theory, right? Vacuum state has the standard momentum k bar and helicity h naught. I mean, for this Fock space constructed out of Q dagger states. But of course, vacuum of the full theory is the vacuum, I mean, with no particles.
Right. Yeah. Fine. Thanks.
Are there any other questions?
Subbu, I should tell you that you have 5 minutes left.
Yeah, I know. Yeah.
Okay, I have a naive question here. So let's say considering n equal to 1, h0 equal to 2, this case, I mean, cannot you act by q the supercharge further such that you go beyond 3 by 2, meaning after 3 by 2 you will probably have 1, right? And then cannot that form a part of the multiply? Or
no, okay. So that is because like basically we are doing one step, okay, because of this reason that I explained earlier, which is if you consider a tensor, right? Okay.
Yeah.
One sec, it's coming up. There's a lot of lag. So if you consider a tensor, okay, of which is antisymmetric in all these I indices, right? The maximum you can construct is till n, okay? So for n is equal to 1, that is just 1. So you can apply the Susi generator only once. The second time, due to anti-commutation relations, you can't have a non-trivial action, okay? Because there is only one supersymmetry charge, right? If it acts twice, it will just give 0 because it anti-commutes with itself.
Okay.
Yeah.
Yeah, thanks.
Okay, when we do like n is equal to 2, if you do the same counting, you will do 2 steps. Like you will go from let us say h naught is equal to -2 minus 3 by 2 to -1. Okay, so that is why you have graviphoton here. Okay, because you could do 2 steps. You can act the charges, the creation operators twice. So you can create spin 1 states, which is the graviphoton. Okay. So I just say what we will do in the next lecture, and then we can take questions and so on. So what I will do is there is something called as HLS theorem, okay, which states that, and this is the graded Lie algebra extension of Coleman-Mandela theorem. It says that if you have n spinor charges, okay, in an interacting quantum field theory, interacting QFT, this implies it has n extended. Whatever supersymmetry algebra we defined is called n extended supersymmetry. So it has an extended Susi algebra. So using this, what I will do is I will write the n is equal to 1 super Yang-Mills action, and I will write, I'll propose a current, and we will verify that it is conserved. And because it has a conserved current, which is a fermion, and it's an interacting theory, we will say that it has n is equal to 1 supersymmetry. That is the approach we will take, because this is the simplest way to establish supersymmetry, and it will allow us to go further quicker. Okay, and earlier all these goof-ups that I was mentioning, what I was doing is like this H0 you can consider in either positive and negative. I think in my notes I did it one way, and here I am doing it the other way, so that is the source of the confusion. But it will be fixed in my notes. I'll explain it better by tomorrow. Are there any questions?
I think first let us thank Subbu for this wonderful lectures. You can unmute yourself and clap or use the button. So if there are any pressing questions, we will have it now before we stop the recording. Otherwise, we can stop the recording and people can ask questions for 10-15 minutes more. Okay, I guess then we will pause the recording for here today, and you can ask any informal questions after it.